For centuries, our view of planets has been limited to the familiar orbs within our own solar system. However, as our telescopes peer further into the cosmos, we're discovering a universe far more bizarre and intriguing than we could ever have imagined. Join us as we venture beyond the ordinary, delving into some of the most extraordinary and unnervingly hostile planets found across the galaxy. One such planet is HD 18973b, a world that seems to glow with a mesmerizing blue hue. This striking color is in stark contrast to the violent storms that rage across its atmosphere. The blue shade, though beautiful, is not as serene as it may appear. It's the result of silicate particles suspended in the planet's thick cloud cover, scattering light in a manner that produces a sky color somewhat like that of Earth. But this alluring visual is deceiving, for HD 18973b is anything but tranquil. The weather on this distant planet is catastrophic. The atmosphere is relentlessly violent, with wind speeds exceeding 2,000 miles per hour, more than 10 times faster than Earth's most powerful tornadoes or hurricanes. These torrential winds carry clouds of silicate dust, creating a hostile environment where rain doesn't fall as droplets but as sharp, glass-like shards. Imagine, if you will, a storm that doesn't gently wash the world, but instead rains down fragments of glass that could slice through anything in its path. The planet's proximity to its host star exacerbates the already extreme conditions. On the day side of HD 18973b, temperatures soar to more than 2,000 degrees Fahrenheit. This intense heat, combined with the thick, swirling clouds and relentless winds, creates a world that is, by any measure, brutal. It's a planet where the atmosphere is constantly shifting, changing at a pace that's almost impossible to predict. Scientists believe the planet's rapid rotation and its violent atmospheric dynamics are key factors in the creation of its chaotic weather systems. These winds are so fast and so destructive that they can continuously batter the surface without respite. The blue hue that once seemed serene is now revealed as a deceptive veil, hiding the true nature of the planet's unrelenting fury. In contrast to the wild weather, we might think of Earth's most extreme storms as being destructive. However, on HD 18973b, the winds are not merely destructive, they're catastrophic. To give you a sense of scale, on Earth, the most intense tornadoes reach wind speeds of about 200 miles per hour. The winds on this planet are 10 times that speed, with gusts that don't dissipate but persist, relentlessly battering the surface. HD 18973b's atmosphere is highly charged, dynamic, and unforgiving, constantly shifting and adapting to the extreme conditions. And while its striking blue hue may seem inviting at first glance, it's an illusion, a mask for the planet's unrelenting storms, with temperatures and winds that challenge the imagination. This is a world where the laws of nature take on an alien intensity, showing us just how vast and unpredictable the universe can be beyond the familiar boundaries of our own solar system. The winds on HD 18973b carry intense heat, creating a harsh and turbulent environment where silicate particles are suspended in the atmosphere. These particles are a crucial element in shaping the planet's eerie blue hue, while also fueling its relentless storms. Unlike Earth's storms, which bring rain and thunder, the extreme conditions on this distant exoplanet lead to a completely different form of precipitation. Rather than water, the planet experiences a terrifying rainfall of sharp silicate glass. This glass rain paints a picture of an utterly inhospitable world. Earth's storms, while fierce and capable of wreaking havoc, still operate within a temperature and pressure range that sustains life. By contrast, HD 18973b's apocalyptic conditions serve as a stark reminder of just how varied and extreme planetary weather can be across the universe. The very concept of glass rain on this alien world fascinates scientists, offering a glimpse into the peculiar weather systems of far-off realms. The silicate particles that make up the rain on HD 18973b are formed under the planet's unique atmospheric conditions. The blistering heat causes silicates to exist in a gaseous state, which then condenses as the atmosphere cools in the upper layers. Intense winds whip these particles across the turbulent sky, causing them to collide and coalesce before they fall back to the surface as glass-like shards. This precipitation is a direct result of the planet's extreme weather patterns. where temperatures swing dramatically between the planet's day and night sides. On the day side, relentless exposure to the nearby star generates searing heat, while the night side experiences a rapid and drastic cooling. This sharp temperature contrast is crucial in facilitating the condensation of the gaseous silicates. However, the planet's atmosphere is not cold enough to form liquid rain. Instead, it cools just enough to cause the gaseous particles to condense into tiny, razor-sharp shards of glass. As these shards descend through the atmosphere, they can potentially reach the planet's surface, presenting a terrifying threat to anything unprotected. The formation of glass rain starkly illustrates how destructive forces can exist alongside life-sustaining processes in the universe. This extreme weather stands in stark contrast to Earth's temperate climate, where the processes that create precipitation are capable of sustaining life. On HD T973b, however, it is the conditions themselves, uninhabitable and volatile, that give rise to such a dangerous phenomenon. The planet's weather patterns challenge our understanding of what constitutes precipitation, forcing scientists to rethink the very nature of weather beyond our own planetary experiences. In the broader context of scientific exploration, the glass rain on HD 19733b is not just a captivating curiosity, it is a vivid reminder of the universe's boundless variety. It encourages a sense of wonder and pushes the limits of human understanding as researchers delve deeper into the meteorological phenomena of distant worlds. The study of such alien weather systems provides invaluable insight into the composition of planetary atmospheres and expands our comprehension of the diverse environments in which life, if it exists, might survive. For any human unlucky enough to be caught on this hostile planet, the glass rain would pose an immediate and lethal threat. As the silicate shards fall, they are propelled at incredibly high speeds by the planet's furious winds. A single shard striking an unprotected human body could cause catastrophic injuries. These particles would act as sharp projectiles, cutting through flesh and organs, resulting in deep lacerations and extensive internal damage. In the scorching temperatures of HD 19733b, any exposed skin would suffer severe burns, making survival impossible without proper protection. The nature of this alien rainfall is far from anything we experience on Earth. It is not a gentle shower, but rather a violent storm of glass, a deadly cascade that could shatter human bodies in seconds. No amount of protective clothing or gear could effectively withstand the force or sharpness of this precipitation. On HD 19733b, the concept of rain is far more sinister, a reminder that the universe harbors environments where life and death are shaped by extremes beyond imagination. The hostile environment of HD 1897333b is nothing short of catastrophic, where the intense heat-violent winds create a reality so extreme that human survival is inconceivable. The atmosphere, far from being a refuge, is a deadly mix, uninhabitable by any terrestrial life form. The very air we would attempt to breathe is filled with silicate particles, which could inflict severe respiratory damage if inhaled, further adding to the planet's dangers. Yet, perhaps the most striking feature of this world is the phenomenon of glass rain, an eerie reminder of just how brutal and inhospitable some exoplanets can be. It emphasizes the narrow boundary between what we deem livable and unlivable in the vast expanse of the cosmos, a boundary that even advanced technology would struggle to cross. The atmosphere of HD 1897333b is a volatile, unpredictable force. Its dangerous nature is driven by a complex set of factors, each contributing to an environment where nothing human could endure for long. At the heart of this violence lies the planet's proximity to its host star. Being so close, the planet is exposed to blistering temperatures, creating an atmosphere charged with thermal energy. This relentless heat fuels turbulent weather systems, pushing the planet into a perpetual state of chaos, where wind and temperature are in a constant battle for supremacy. One of the most unsettling features of HD 1897333b is its rapid rotation. With a complete rotation taking only a single day, the planet is subject to drastic temperature shifts between its day and night sides. The day side, facing directly towards the star, is scorched by extreme heat, while the night side plummets into icy coldness. This sudden temperature difference creates enormous pressure systems that unleash fierce winds, propelling the atmosphere into violent, unpredictable motion. But perhaps the most dangerous aspect of this extreme environment is the presence of clouds laden with silicate particles. These particles, which give the planet its distinctive blue hue, are responsible for one of the most perilous weather phenomena: glass rain. When the wind speeds reach their peak and conditions shift, these silicate particles condense and are forced downward at terrifying speeds. The result is a lethal downpour of sharp, glass-like shards. Combined with the already destructive winds, this phenomenon makes the atmosphere of HD 189733b a place where survival is not merely unlikely, it is impossible. Even the most advanced technologies designed for exploration and discovery would find themselves ill-equipped to withstand such conditions. HDE 9733b, with its combination of extreme heat, violent winds, and deadly glass rain, serves as both a captivating enigma and a sobering reminder of the untold challenges humanity would face in exploring the universe. The planet stands as a testament to the raw power of nature in the cosmos, underscoring just how finely tuned the conditions for life on Earth truly are. As we look toward the stars, HD 189733b paints a vivid picture of what awaits in the darker corners of space, an environment that is as awe-inspiring as it is utterly lethal. Furthermore, the atmosphere of HD 189733b is a furnace of high-energy processes, where complex chemical reactions occur at a relentless pace. These reactions contribute to a brutal and unpredictable climate, one that seems designed to test the limits of exploration. The constant churn of the atmosphere, punctuated by violent storms and ever-shifting weather patterns, creates an environment where no mission can afford to overlook the danger. Here, extreme temperature fluctuations, hazardous materials, and the constant risk of fast-changing, violent weather converge to create a world where survival is a challenge at every turn. This cocktail of volatile factors establishes HD 189733b as one of the most perilous planets known to us, an alien world that showcases the very extremes of atmospheric dynamics beyond the confines of Earth. Orbiting extraordinarily close to its host star, the planet is exposed to extreme environmental conditions. This proximity funnels an overwhelming amount of energy onto the planet, heating its day side to a staggering 2,000 degrees Fahrenheit. Such searing heat creates a stark contrast between the blistering, sunlit day side and the significantly cooler, perpetually dark night side. The result? A vicious cycle of weather patterns and pressure systems locked into a constant, unyielding rhythm. On the day side, the relentless heat turns the landscape into a vast, inhospitable expanse. The atmosphere undergoes rapid thermal expansion, leading to violent winds that can tear across the surface at speeds that defy typical planetary weather. It's an environment where heat doesn't just scorch. It powers dynamic forces that drive the formation of silicate-rich clouds. As these clouds churn and roil, they fuel some of the most powerful storms imaginable, a continuous tempest that reshapes the atmosphere in an ongoing frenzy. The constant influx of energy from the star means that air near the surface is constantly trying to rise and dissipate. This constant updraft, combined with the overwhelming heat, causes turbulence that feeds chaotic, unpredictable flow patterns. The result is a storm system that can unleash winds exceeding 2,000 miles per hour, with the planet's atmosphere acting as a swirling, unstable pressure cooker. This extreme interaction between heat, wind, and pressure turns the entire atmosphere into a dynamic and perilous system, constantly in flux, forever dancing to the pulse of solar energy. HD 17733b's proximity to its star is the spark that fuels this unrelenting weather chaos. The star's unyielding heat causes complex interactions between wind, heat, and pressure, generating an atmosphere that is a living, breathing entity, constantly shifting, constantly changing. In this way, the planet becomes a showcase for the power of stellar influences on planetary climates, revealing what could be the outer limits of solar-driven planetary dynamics in the universe. On the surface of HD 189733b, during a glass rainstorm, the spectacle would be as stunning as it is terrifying. With one side of the planet always facing the star, the day side would glow with a surreal, bluish light, refracted through thick clouds heavy with silicate particles. The atmosphere would be an ever-shifting canvas of deep blues and vibrant hues, with swirling storm clouds constantly shifting and reshaping above. As the glass rain begins to fall, the true danger becomes apparent. This is no gentle drizzle. The precipitation consists of sharp, jagged silicate shards that plummet toward the surface at lethal speeds. Instead of the soft rain we know on Earth, the glass rain would create a dangerous, dazzling spectacle, glimmering shards reflecting the ambient light as they fall. The atmosphere, thick with the presence of these deadly fragments, would limit visibility to mere inches, shrouding the landscape in a mist of refracted light and swirling particles. What's more, the winds sweeping across the surface would only add to the peril. With gusts reaching incredible speeds, any view of the sky would be filled with the thick, chaotic mist of silicate rain, refracting light in mesmerizing patterns but obscuring the cosmos beyond. The landscape would be forever in flux, locked in a violent, never-ending struggle between the extreme forces of heat, wind, and pressure. HD 189733b, in all its brutal beauty, stands as a reminder of the raw, untamable power of the universe. The winds of HD 189733b whip violently through its atmosphere, creating a surreal spectacle as shards of glass are swept into the turbulent air. The sky itself seems alive, swirling in a vortex of danger and beauty, a mesmerizing yet deadly dance of nature. Despite the stunning visual display, the underlying terror of this hostile environment is undeniable. Every glimmering shard of glass that rains down serves as a grim reminder of the planet's inhospitable conditions, unlike the cozy storms of Earth that bring life-giving rain. Here, the sky pulses with a vivid, threatening energy, reflecting the volatile nature of this distant world. Yet, despite the perilous atmosphere of HD 189733b, scientists have found innovative ways to study such extreme alien environments. Researching distant and hostile planets like this requires advanced techniques and cutting-edge technology, allowing us to gather valuable data even when faced with seemingly insurmountable challenges. One of the primary methods for exploring exoplanets is through the use of space telescopes that analyze the light emitted or reflected by these far-off worlds. Instruments such as the Hubble Space Telescope and the upcoming James Webb Space Telescope employ spectroscopy to break down light into its component wavelengths. This process reveals crucial information about a planet's atmosphere, unlocking secrets that would otherwise remain hidden. By studying the way a planet passes in front of its star, scientists can measure the light that filters through its atmosphere during a transit. This allows them to detect the presence of molecules and particles that tell us about the planet's atmospheric composition, temperature, and even its cloud structures. For instance, the distinctive signature of silicates in the atmosphere of HD 189733b can be identified through this method, giving us insight into the glass rain that defines the planet's alien weather patterns. Numerical models and simulations also play a pivotal role in our understanding of exoplanets. By inputting observational data and applying existing knowledge of atmospheric physics, scientists can create complex computer models to simulate the extreme conditions on distant worlds. These models help predict weather patterns, temperatures, and atmospheric dynamics, offering a glimpse into the unpredictable nature of such alien environments. This approach allows us to make educated predictions about the weather and climate of exoplanets like HD 18973b, even when we can't directly observe them in real time. Collaboration between various scientific fields further enriches our understanding of these distant planets. Astronomers, atmospheric scientists, and planetary scientists often work together, pooling their expertise to enhance the quality of their research. By sharing findings, hypotheses, and methodologies, this interdisciplinary approach fosters a deeper and more nuanced understanding of the cosmos. It allows scientists to connect their observations to larger theories about planetary formation, habitability, and the diversity of conditions across the universe. Ultimately, the combination of observational data, advanced simulations, and collaborative efforts continues to expand our knowledge of scientists. Scientists are working tirelessly to understand how planetary systems and life might function across the universe, even in the most extreme environments, like that of HD 1899733b. This alien world serves as a prime example for understanding the formation and evolution of hot Jupiters, a class of exoplanets known for their immense size and close proximity to their stars. HD 19733b provides crucial insights into the processes that govern the development of such gas giants. One of the key concepts studied in this context is planetary migration, the theory that these massive planets originally formed farther from their stars and gradually moved inward to their current positions. Observations of HD 1897333b, with its rapid orbit and extreme atmospheric conditions, deepen our understanding of how hot Jupiters interact with their environments. These findings also suggest that the intense internal heating caused by the planet's proximity to its star plays a significant role in shaping its atmosphere and weather patterns. By studying planets like HD 19733b, scientists are able to better understand the factors that influence atmospheric dynamics. This includes the distribution of heat across the planet, the composition of its atmosphere, and how these factors come together to form the planet's unique climate. Insights gained from this research are critical not only for understanding the life cycles of gas giants, but also for expanding our knowledge of the diverse range of planets that populate our universe. The discovery of silicate clouds and glass rain on HD 189733b marks a groundbreaking moment in the study of exoplanets, revealing the incredible complexity of planetary atmospheres under extreme conditions. These findings challenge our current models and invite astronomers to reconsider how different elements and compounds behave in such high-temperature environments. The presence of silicate clouds and glass rain on this distant world pushes the boundaries of what we know about planetary chemistry, suggesting that under the right conditions, elements we thought were inert or unreactive may undergo fascinating transformations. As researchers probe these extreme conditions, it becomes clear that HD 19733b is not just an anomaly, but a vital testing ground for understanding gas giants across the universe. By comparing its features with other exoplanets, scientists are able to build a more nuanced understanding of the diversity of planetary systems and the forces that shape them. This is more than a matter of curiosity. Studying planets like HDT 9733b refines our models of planetary formation and evolution, offering valuable insights into the birth and development of hot Jupiters. These revelations help improve our understanding of how gas giants come into being and continue to evolve, not just within our own solar system, but across the cosmos. However, the prospect of establishing a human presence on HD 18973b raises many formidable challenges, all of which stem from the planet's harsh and unwelcoming environment. The first hurdle is the extreme atmospheric conditions. Winds on this planet can exceed speeds of 2,000 miles per hour, a relentless force that would require any potential base to be extraordinarily robust. Beyond the high-velocity winds, the planet's surface is bombarded by glass rain, silicate shards hurtling through the atmosphere at incredible speeds. To survive in such an environment, any structures would need to be built with advanced materials capable of absorbing and deflecting these glass shards, offering a level of protection we can scarcely imagine today. Moreover, the temperature extremes on HD 19733b would be another monumental challenge. With surface temperatures reaching upwards of 2,000 degrees Fahrenheit, any base would need to be equipped with highly advanced thermal insulation and temperature regulation systems. Life support systems would also have to work overtime, ensuring a stable and breathable atmosphere within the base while managing the risks posed by the heated, volatile air outside. The possibility of chemical reactions in the high-temperature environment would require careful monitoring and proactive management. Radiation, too, would pose an enormous threat. Unlike Earth, HD 1897333b lacks a protective magnetic field, leaving any exposed structures vulnerable to intense stellar radiation. Engineers would need to develop specialized shielding to safeguard human inhabitants from the harmful radiation emitted by the planet's nearby star. This would not be a simple task. Calculating the correct type and amount of protective materials would require careful precision, as the radiation levels are far more dangerous than what we experience here on Earth. Finally, The logistical challenges of establishing a base on HD 18973b are staggering. Given the planet's extreme distance from Earth, transporting personnel, equipment, and supplies would be a monumental task in itself. The need for a self-sustaining base would become paramount. To survive, such a base would need to be capable of extracting resources from the hostile environment, generating power, recycling water, and producing food on site. Without the ability to rely on regular resupply missions, the technology needed to establish a viable, long-term habitat on HD 18973b would have to be nothing short of revolutionary. In sum, the vision of a human base on HD 19973b is not just a matter of technological innovation. It represents a complete rethinking of what is possible in extreme environments. Overcoming these challenges would require breakthroughs in material science, life support technology, energy generation, and resource management. The implications of such advancements extend far beyond this distant exoplanet, offering potential solutions for humanity's long-term survival, whether on Earth or on other planets. In stark contrast to HD 18973b, the exoplanet WASP-12b offers a glimpse into a different kind of extreme environment, shaped by its tight orbit around its parent star. Orbiting at just about 1 million miles from its star, roughly 1/8 of the distance between Earth and the Sun, WASP-12b's year lasts only 1 day. In that incredibly short period, the planet completes a full orbit, subjecting its surface to relentless stellar radiation and resulting in temperatures that can exceed 2,000 degrees Fahrenheit. This intense heat fuels a volatile atmosphere rich in gaseous molecules that would not be stable under cooler conditions. As a result, the atmosphere of WASP-12b is in a constant state of flux, with extreme weather and atmospheric disturbances likely to be commonplace. The planet's proximity to its star makes it one of the most extreme exoplanets known, offering researchers a unique opportunity to study the effects of such close encounters with a stellar body. By examining the conditions on WASP-12b, scientists can better understand the interplay between stellar radiation, planetary atmospheres, and the ways in which planets evolve under intense environmental pressures. Moreover, the gravitational forces at play create a fascinating tidal interaction between WASP-12b and its star, leading to the dramatic deformation of the planet. This unique phenomenon causes the planet to take on an oblate shape, meaning it bulges significantly at the equator. The immense tidal pull from its parent star stretches the planet, influencing not only its appearance, but also its internal dynamics, contributing to an unstable atmosphere. These tidal forces, combined with extreme heat and pressure, spark some of the most extraordinary atmospheric phenomena in the universe, including the potential for the gradual loss of the planet's atmosphere. The intense stellar winds further exacerbate this effect, stripping away its outer layers over time. As WASP-12b continues its orbit, it may be losing material to space, a process driven by the unequal heating and gravitational interaction with its star. This ongoing transformation provides vital insights into the evolution of planets that orbit perilously close to their stars. WASP-12b's oblate shape is a direct consequence of the extreme gravitational pull exerted by its parent star. Orbiting just about 1 million miles from the star, the planet is subjected to overwhelming tidal forces that distort its structure. This gravitational interaction results in a dramatic bulging at the equator, a distortion not typically observed in most planets. While many planets maintain a roughly spherical shape, the immense proximity of WASP-12b to its star leads to tidal forces so powerful that they stretch the planet outward at its equator, creating the pronounced shape that distinguishes it from other exoplanets. This deformation is more than just a visual oddity. It profoundly affects the planet's internal dynamics. The tidal heating produced by these gravitational interactions raises surface temperatures to extreme levels, fostering complex atmospheric behavior. The ongoing stretching of the planet contributes to the maintenance of a dynamic, unstable atmosphere, where high temperatures facilitate the atmospheric loss, making WASP-12b even more alien and unusual than most planetary bodies. The extraordinary oblate shape of WASP-12b, alongside the processes that lead to its formation, sheds light on the intricacies of planetary evolution, especially for those that orbit extremely close to their stars. The study of exoplanets like WASP-12b enhances our understanding of the tidal forces at play in the cosmos, offering a glimpse into the many types of planetary systems scattered across the universe. These observations enrich our knowledge of how gravitational interactions between a planet and its star can reshape and even destabilize the entire planetary system. WASP-12b is also undergoing a staggering rate of atmospheric loss, a direct result of its extreme proximity to its parent star. Research indicates that the planet is shedding atmosphere at an alarming rate, equivalent to roughly 100 million tons each year. This rapid atmospheric stripping is driven primarily by the powerful stellar radiation and gravitational forces that steadily tear away the outer layers of the planet's atmosphere. Given the scale of this loss, projections suggest that WASP-12b may only have a few million years left before it is consumed entirely by its star. This time frame is incredibly short by astronomical standards, marking the planet's rapid decline. As atmospheric loss continues, WASP-12b will likely undergo dramatic changes, becoming an unrecognizable remnant of its former self. In its final stages, it may be completely obliterated, a testament to the extreme forces at play in close-orbit planetary systems. The ongoing process of atmospheric stripping on WASP-12b offers a vivid example of the vulnerabilities of planets caught in close orbits with their stars. It highlights the intense environmental pressures these worlds face, providing astronomers with critical insights into the life cycles of planets that endure such hostile conditions. Observing WASP-12b not only deepens our understanding of this specific exoplanet, but also offers broader implications for similar worlds scattered across the universe, shedding light on the fate of planets that exist under the harshest conditions imaginable. Through ongoing research, scientists are striving to uncover the factors that shape the evolution of planets subjected to extreme conditions. One such planet, WASP-12b, stands as a fascinating example of this dynamic process. Orbiting perilously close to its parent star, this exoplanet offers an extraordinary view of the sky, one that would appear drastically different from anything seen on Earth. From the surface of WASP-12b, the sky would unfold as an otherworldly and vibrant spectacle, influenced heavily by the planet's intense proximity to its star. The star, looming close to the horizon, would dominate the view. Its intense glow would cast a surreal light over the planet's landscape, creating an atmosphere unlike anything in our own solar system. Depending on the time of day, the star might appear as a blinding orb, perhaps surrounded by a vivid spectrum of colors, ranging from brilliant whites and yellows to fiery oranges. These hues, intensified by the extreme conditions, would result from the star's light refracting through the planet's thick, volatile atmosphere. This atmosphere would be anything but static. Composed of swirling gases and various chemical compounds, it would be in a constant state of flux, shaped by the planet's extreme heat and rapid winds. The intensity of the heat, combined with the violent winds, would give rise to frequent, unpredictable storms. These storms could reshape the appearance of the sky in mere moments, while complex cloud formations would swirl above, tinged with deep blues and reds due to chemical reactions unfolding in the high-temperature environment. Given the scorching temperatures, estimated at around 2,000 degrees Fahrenheit, roughly 1,100 degrees Celsius, the atmosphere itself might glow faintly with a luminescence of its own, adding to the surreal quality of the sky. This visual spectacle, while breathtaking, would also be fraught with danger. The intense stellar radiation would make the environment highly inhospitable, preventing human exploration and posing significant challenges for any potential probes sent to study the planet up close. The surface would be a harsh, unforgiving place where no form of earthly life could survive. Opinions about the visibility of distant stars in the atmosphere of WASP-12b remain uncertain. The dense cloud cover, coupled with the overpowering brightness of the parent star, would obscure much of the night sky, making stargazing an extremely rare event. Once the star set, the planet's atmosphere would likely remain shrouded in a thick veil of clouds and gases, creating a near impossible task for observers hoping to see beyond the atmospheric haze. Thus, the view of the night sky would be a fleeting, challenging experience, with little to be seen beyond the overwhelming glow of the star. Yet, Despite its inhospitable nature, the visual impact of WASP-12b's sky would be undeniable. It would be a striking juxtaposition of beauty and danger, offering profound insight into the extreme conditions that define planets in close orbits around their stars. This planet serves as a testament to the relentless forces at play in the universe, where beauty and peril often exist in precarious balance. WASP-12b is one of the hottest exoplanets ever discovered, with surface temperatures soaring to around 2,500 degrees Celsius, about 4,500 degrees Fahrenheit. At such scorching temperatures, the planet's surface would be a hostile wasteland, where most materials, including metals like iron and copper, would not exist in their solid or liquid states. Instead, they would be vaporized into gas, leaving behind a barren landscape without the traditional solid structures we associate with Earth. Even elements with high melting points, such as lead, would be reduced to vapor in the extreme heat of WASP-12b's surface. In the context of exoplanetary studies, WASP-12b offers a glimpse into the forces that govern the evolution of planets under extreme stellar conditions. Understanding these conditions can help scientists gain deeper insight into how planets and the life, or lack thereof, they might support, develop in such a hostile environment. This planet not only challenges our understanding of habitability, but also sparks questions about the resilience of life in the face of such extreme forces. The more we learn about WASP-12b, the more we uncover about the boundaries of existence beyond our own solar system. The extreme environment of WASP-12b leads to a fascinating array of atmospheric phenomena that are both extraordinary and mysterious. In this alien world, the atmosphere is primarily composed of exotic gases, including sodium and potassium, which can only remain in their gaseous forms under the scorching temperatures that define this planet. These gases not only shape the planet's physical characteristics, but also give it an eerie glow, as they reflect the light from the star it orbits. This glow, subtle yet mesmerizing, provides a glimpse into the planet's hostile yet captivating nature. WASP-12b serves as a stark reminder of the incredible diversity in planetary environments that exists within our universe. It offers an unparalleled opportunity to explore how various factors, such as a planet's proximity to its star and the composition of its atmosphere, can dramatically alter its characteristics. With its dense, volatile atmosphere made up of elements like hydrogen, helium, sodium, and other reactive compounds, WASP-12b is one of the most extreme examples of this diversity. The planet's proximity to its star results in intense heating, which fuels violent weather patterns, further distinguishing it from planets we know in our own solar system. As WASP-12b orbits its star, it is in a constant state of flux. The relentless gravitational pull and the unyielding radiation from its star are gradually stripping away the planet's outer layers. Over time, this process causes the lighter elements in the atmosphere to escape into space, propelled by the fierce stellar winds and radiation. The planet's atmosphere, once a rich blend of gases, is now increasingly depleted, losing much of its mass and stability. These processes, driven by the planet's close orbit and the intense stellar environment, are gradually reshaping WASP-12b into a dramatically different world. In addition to the atmosphere's thinning, the surface of WASP-12b is likely undergoing significant transformations. The extreme heat causes the vaporization of heavier molecules, leaving the planet with a much less dense and more unstable environment. These changes are of great interest to researchers as they offer valuable insight into the long-term evolution of exoplanets, specifically hot Jupiters like WASP-12b. Understanding how these materials interact, change, and eventually escape into space can unlock vital clues about the broader life cycle of planets subjected to extreme conditions. WASP-12b provides a rare opportunity to study the dynamics of planetary atmospheres under such extreme pressures. With each new observation, scientists are piecing together how planets and stars interact under the harshest of conditions. These interactions reveal how environments like those of WASP-12b evolve over time and the lasting consequences they have on the materials that once made up the planet. In essence, WASP-12b is a living laboratory that helps us understand not only the future of similar planets, but also the very forces that govern the evolution of worlds in our galaxy. The planet's dramatic atmospheric changes are largely due to the immense gravitational pull of its host star. As WASP-12b orbits so closely to its star, tidal forces stretch and distort the planet's shape. This deformation causes a gravitational gradient across the planet, meaning atmospheric particles experience varying forces depending on their proximity to the star. In such an environment, lighter gases are far more likely to escape into space. When these gases reach speeds sufficient to overcome the gravitational pull, they are lost to the vacuum of space in a process known as atmospheric escape. This phenomenon is particularly pronounced in hot Jupiters like WASP-12b, where extreme heat and radiation facilitate the loss of atmospheric material at an alarming rate. Each of these processes contributes to the ongoing transformation of WASP-12b. As the planet sheds its atmosphere and undergoes intense shifts in its composition, it becomes a unique case study in the ongoing research into the formation and evolution of exoplanets under extreme conditions. The gravitational pull of stars plays a vital role in shaping the fate of a planet's atmosphere, and the impact on WASP-12b is a prime example of this cosmic tug-of-war. The immense gravity from the star doesn't just draw the planet closer, it also indirectly affects the temperature of the atmosphere. The intense heat from the star raises the temperature of the surrounding gases, initiating a complex process. Not only do these gases warm, but they also undergo ionization, transforming atoms and molecules into charged particles. This ionized state, combined with the relentless pressure exerted by the star's radiation, causes atmospheric materials to be pushed away from the planet at an accelerated rate. The result? An ongoing loss of atmosphere, one that is exacerbated by the gravitational pull. This intricate balance of forces between a star's gravity, a planet's atmosphere, and the radiation pressure offers a vivid illustration of celestial mechanics in action. It's a striking example of how the evolution of a planetary body can be framed by the forces at play between the planet and its star. For WASP-12b, this dynamic is crucial in determining how much of its atmosphere remains intact. As it continues to interact with the immense gravitational and radiative forces exerted by its distant sun, the composition of the planet's atmosphere constantly evolves. Studying WASP-12b provides invaluable insights into the life cycles of planets, especially those in close orbits around their stars, commonly referred to as hot Jupiters. These planets, like WASP-12b, provide a fascinating window into how proximity to a star can influence a planet's atmospheric composition, thermal dynamics, and ultimately its fate over time. One of the most critical aspects that scientists focus on is atmospheric escape, the process through which materials are lost from a planet's atmosphere due to the intense gravitational pull and radiation from its host star. By observing this, researchers can deepen their understanding of how atmospheres on similar exoplanets evolve. This knowledge has far-reaching implications, helping to predict how other planets might evolve during their early stages when they are still subject to intense external forces. Beyond this, the extreme conditions present on WASP-12b provide a unique opportunity to study the factors that determine whether a planet can retain its atmosphere for a significant period. The chemical composition of the planet, constantly altered as it loses gases, offers critical clues about planetary evolution. Understanding these changes allows scientists to track a planet's journey from formation to its eventual stages, including the possibility of transitioning into atmosphereless bodies, similar to Mercury or the Moon. The environment of WASP-12b and its ongoing interaction with its star acts as a miniature model of planetary evolution, offering a glimpse into how planets in general may change over time. By examining how such planets evolve, scientists can develop models that apply to a much broader range of planetary systems. This not only enhances our understanding of WASP-12b, but also expands our knowledge of planetary life cycles throughout the universe. Imagine for a moment that a spacecraft could endure the extreme heat of WASP-12b's atmosphere. Upon entering the turbulent upper atmosphere, it would encounter a dynamic and volatile environment that is starkly different from anything found on Earth. This atmosphere is a chaotic mix of high-energy gases, including hydrogen, helium, sodium, and various ionized elements, all present due to the scorching temperatures, which can exceed 2,500 degrees Celsius. At such temperatures, many materials exist in a vaporized state, swirling in a gaseous form. As the spacecraft penetrates deeper into the upper atmosphere, it would experience fluctuating pressure and density levels. Unlike Earth's stable atmosphere, the one on WASP-12b is highly dynamic, made up of shifting layers that constantly evolve due to thermal dynamics and the relentless radiation from the host star. This constant motion creates turbulent wind patterns that would make navigation and stability a serious challenge for the spacecraft. The atmosphere on WASP-12b is anything but uniform. It's in a state of perpetual flux, driven by forces beyond our comprehension. In addition to the challenging winds, the spacecraft would likely detect unusual chemical reactions within the atmosphere. Stellar radiation can lead to the formation of energized particles, producing spectacular displays of light. For example, elements like sodium and potassium, abundant in the atmosphere, can absorb and re-emit stellar radiation, creating bright, glowing trails that streak across the sky. These elements, when energized, form vibrant colors that illuminate the atmosphere in a breathtaking display. The radiation and resulting ionization processes give the atmosphere a surreal, otherworldly appearance, one that feels almost like an alien dream, shaped by forces far beyond our planet's reach. By studying WASP-12b and similar exoplanets, scientists are not only peering into the heart of extreme planetary environments, they are also unraveling the mysteries of how planets evolve, how atmospheres change, and how stars sculpt the very futures of their planetary companions. Every observation made on this distant world has the potential to reshape our understanding of the universe and its vast, complex systems. The atmosphere of distant exoplanets presents an array of fascinating phenomena that challenge our understanding of planetary processes. One such phenomenon is the ability of certain metals, which on Earth are typically solid or liquid, to remain suspended in the gas phase due to extreme temperatures. This remarkable process allows metals to condense into vapor forms that float high in the atmosphere. Observing these phenomena on exoplanets could offer groundbreaking insights for scientists, helping them unravel atmospheric behaviors that are impossible to study here at home. By investigating these unusual environments, researchers can gain a deeper understanding of how planetary atmospheres function in extreme conditions, far beyond anything we see in our solar system. Take, for example, the fate of WASP-12b. This exoplanet's future sharply contrasts with that of Earth and the other planets in our solar system, underscoring the diverse outcomes that await planets depending on their specific conditions. WASP-12b's close orbit around a very hot star leads to an ever-increasing loss of its atmosphere. This process, driven by stellar forces, is expected to continue until the planet is gradually stripped of mass, making it barren and transforming its characteristics entirely. In our own solar system, the planets, including Earth, orbit the Sun at varying distances, influenced by a different set of factors. Scientists project that in the next several billion years, as the Sun exhausts its nuclear fuel, it will enter the red giant phase. During this phase, the Sun is expected to expand, potentially engulfing the inner planets, including Earth. This expansion will drastically alter their structures and atmospheres. The outer planets may experience shifts in their orbits due to the mass loss of the Sun, as it sheds its outer layers and grows increasingly unstable. However, the fate of our solar system is more gradual compared to the swift and intense atmospheric loss seen on WASP-12b. While the exoplanet faces immediate drastic changes, planets in our solar system will undergo a slow, long-term evolution over eons. This offers a more stable environment in the interim, allowing for a deeper study of planetary evolution over extended periods of time. Both scenarios, however, highlight the critical role of a planet's proximity to its star in determining its ultimate fate. By studying WASP-12b and comparing it to our solar system, scientists can gain invaluable insights into how celestial bodies evolve and the numerous paths that planets may follow throughout the universe. It also serves as a reminder that, while some planets are doomed to destruction, others may persist for billions of years, shaped by the unique characteristics of their host stars. Among the many wonders in the universe, there is one exoplanet that has become notorious for its peculiar appearance, TRES-2b, the darkest known planet. Its extraordinary ability to absorb 97% of the light that hits its surface sets it apart from all other celestial bodies. This extreme light absorption results in the planet reflecting very little light back into space, giving it an eerie, almost unnatural darkness. In fact, TRES 2b is even darker than coal or black acrylic paint, a fact that has astounded astronomers and made it a subject of intense study. What makes TRES 2b's darkness so remarkable is its atmospheric composition. Scientists believe that the planet's thick, metallic atmosphere plays a significant role in its light-absorbing properties. The presence of metallic clouds along with vaporized sodium or potassium likely contributes to the planet's ability to trap light. This dense and dark atmosphere is a crucial factor in its minimal reflectivity, allowing almost no light to escape. When compared to other bodies in our solar system, TRES 2b stands out as a true anomaly. While moons like Saturn's Titan and some of the outer planets may appear relatively dark, none exhibit the extreme level of light absorption seen on TRES 2b. This striking darkness has intrigued researchers, prompting further investigations into the exoplanet's unique characteristics. By studying this phenomenon, scientists can explore how different celestial environments evolve and how varying atmospheric compositions contribute to such captivating properties. TRES 2b, in a universe full of vibrant and colorful planets, serves as a stark reminder of the vast diversity that exists among the planets we have yet to discover. The composition of TRES 2b's atmosphere adds further layers to its intriguing mystery. As a hot Jupiter, the planet orbits very close to its star, subjecting it to incredibly high temperatures and creating conditions for unique atmospheric effects. Researchers believe that this intense heat allows certain molecules to trap light across a wide range of wavelengths, further enhancing the planet's darkness. Metallic compounds, including sodium and potassium, likely form thick clouds in the upper atmosphere. These clouds are believed to play a central role in trapping light, absorbing not only visible light, but also extending the effects into the infrared spectrum, diminishing the amount of light that escapes back into space. This combination of factors, the planet's proximity to its star, its unique atmospheric composition, and the presence of light-absorbing compounds, has made TRES 2b a subject of fascination for scientists exploring the extremes of planetary conditions. As we continue to study such exoplanets, we gain a deeper understanding of how atmospheric processes can shape the evolution of distant worlds, each with its own set of incredible characteristics waiting to be uncovered. On the distant exoplanet known as TARES 2b, an intriguing and complex atmosphere takes shape, one that defies common understanding of planetary environments. The thick air surrounding the planet may be teeming with carbon-based compounds, including carbon monoxide and carbon dioxide, both notorious for their strong absorption properties. These components don't just coexist, they interact, triggering complex chemical reactions that form a multi-layered structure, effectively trapping incoming light. It is this unique combination of metals, carbon molecules, and other light-absorbing elements that make TARES 2b not only one of the darkest planets ever discovered, but also one of the most fascinating. Its atmosphere challenges the very concept of what we consider typical planetary behavior. Studying TRES 2b goes beyond just answering questions about this specific world. It has broader implications, contributing to our understanding of atmospheric dynamics in extreme environments. The findings from this exoplanet are crucial to expanding our knowledge of the vast diversity of worlds that exist outside our solar system. Understanding how TRES 2b operates can reveal how atmospheres evolve under extreme conditions and offer new insights into planetary science. One of the most striking features of TRES 2b is its astonishing surface temperature, which can reach around 1,500 degrees Celsius or approximately 2,700 degrees Fahrenheit. This searing heat stems from the planet's close proximity to its star, which floods the atmosphere and surface with intense radiation. However, the true source of its extreme temperature lies in the planet's darkness. TRES 2b absorbs nearly 97% of the light that strikes it, leaving very little to be reflected back into space. In essence, almost all the energy it receives is converted into heat, raising the temperature of the planet to a level that is unimaginable by earthly standards. Unlike planets with reflective surfaces, such as those with snow-covered ice caps that bounce much of the star's light away, Tree S2b retains almost every bit of the incoming energy. This creates an environment where heat is perpetually stored in the atmosphere, causing it to skyrocket. Moreover, the metallic clouds that dominate the planet's sky may also trap heat through a greenhouse effect, adding to the intensity of the heat and creating a harsh, furnace-like atmosphere. The interplay of these factors means that TRAS-2b is not just another hot planet, it's one of the hottest exoplanets ever discovered. The way its atmosphere and surface properties interrelate reveals just how dynamic and varied planetary systems can be. For scientists, TRAS-2b is a living example of the extreme diversity found across the universe. If one were to somehow stand on the surface of TRAS-2b, the experience would be nothing short of surreal. The extreme heat would be overwhelming, around 1,015 to 1,700 degrees Celsius, an environment so scorching that any human being would be instantly fried without the aid of specialized heat-resistant technology. A specially designed suit would be a necessity, just to withstand a brief period in this inhospitable world. Adding to the difficulty of survival is the atmosphere itself, thick with materials that absorb light. This is no ordinary air. It's filled with metallic compounds and vaporized elements that prevent sunlight from illuminating the landscape. The planet would be enshrouded in an eerie darkness dominated by deep shadows rather than the bright, familiar daylight we experience here on Earth. The sun's light would be swallowed whole, leaving almost no illumination. As a result, visibility would be incredibly limited. The environment would be defined by faint, muted hues with little to no light bouncing off the ground or the atmosphere. Human vision, adapted to Earth's shifting light, would struggle in this near-total darkness. Without artificial lighting, it would be nearly impossible to make out any shapes or details, as the overwhelming absorption properties of the atmosphere would absorb whatever feeble light was emitted. This unique and hostile environment paints a vivid picture of extreme heat and unbelievable darkness, a landscape that forces human perception to its limits. It reminds us that exoplanets like TRAS-2b exist in an entirely different realm, one where conditions are so different from Earth's that they seem almost alien. Understanding these worlds helps to expand our concept of what a planet can be, challenging us to rethink the boundaries of planetary environments. Understanding such distant and alien worlds doesn't just happen by looking through telescopes or staring at photos. For planets like 2b, measuring reflectivity, that is, how much light the planet reflects, requires sophisticated methods and cutting-edge technology. One such method is transit photometry, in which a planet passes in front of its star from our viewpoint. This causes a temporary dip in the observed brightness of the star, revealing critical information about the planet. By analyzing the light curve produced during such a transit, scientists can calculate key attributes of the planet, such as its size and its reflectivity. A key measurement in these studies is the albedo of the planet, how much light is reflected back into space. A low albedo, such as that of TRAS-2b, suggests a dark surface that absorbs nearly all of the incoming light, making it an especially challenging object of study. Beyond transit photometry, another critical tool is spectroscopy, which allows researchers to analyze the atmosphere in far more detail. When light passes through a planet's atmosphere during a transit, certain wavelengths are absorbed by the gases present. By studying the spectrum of this light, scientists can uncover a wealth of information about the planet's atmosphere, including its chemical makeup and the complex interactions between different elements. The techniques and tools used to understand TRAS-2b give us more than just a glimpse into the life of a single exoplanet. They expand our understanding of how planets in extreme conditions behave, offering insights into the diversity and complexity of worlds far beyond our solar system. TRAS-2b is just one example of how our universe defies the boundaries of our imagination, an extreme and mysterious world waiting to be explored. In the search for exoplanets, ground-based and space telescopes play a pivotal role in indirectly observing these distant worlds, using various wavelengths of light to detect subtle changes in brightness. These observations not only confirm findings derived from transit data, but also help refine key measurements, such as a planet's reflectivity, temperature, and atmospheric composition. When combined, these methods allow scientists to develop a more complete picture of an exoplanet's physical properties, an incredible feat, considering the vast distances that separate us from these far-off worlds. One such world, TRES 2b, serves as an extraordinary example of the diverse planetary atmospheres found beyond our solar system. This exoplanet, known for its strikingly high temperatures and profound darkness, offers a unique window into the complex dynamics that shape planetary environments. Through the study of TRES 2b, scientists have gained insights into how different conditions, from a planet's proximity to its star to the materials present in its atmosphere, can result in dramatically varied atmospheric compositions and behaviors. At the heart of TRES 2b's mystery lies its extreme proximity to its host star. Orbiting at an exceptionally close distance, TRES 2b is subjected to intense thermal radiation, which influences its atmosphere in ways that are starkly different from those of planets farther away. The planet's tight orbit exposes it to blistering heat, reaching temperatures of up to 1,500 degrees Celsius, an environment that significantly shapes its atmospheric conditions. This extreme heating triggers atmospheric processes such as atmospheric escape, where lighter gases are lost to space, offering a vivid example of how a planet's position in relation to its star can directly impact its atmospheric evolution and long-term stability. TRES-2b also exemplifies the crucial role that light-absorbing compounds play in a planet's thermal properties. In its atmosphere, scientists have discovered metallic clouds and chemical interactions that contribute to the planet's incredible ability to absorb light. This ability to soak up the light from its nearby star rather than reflect it enhances TRES-2b's darkness, helping us understand the mechanisms behind the reflectivity and heat retention of planetary atmospheres. Such findings offer invaluable data that can be applied to other exoplanets with similar characteristics, providing a clearer picture of how a planet's composition can influence its overall climate and thermal behavior. Beyond the specifics of TRES-2b, the study of such extreme exoplanets highlights the remarkable diversity of atmospheres found throughout the universe. By comparing TRES-2b with exoplanets that have very different atmospheric conditions, such as those with thick gaseous envelopes or those with abundant cloud cover, scientists are broadening their understanding of planetary formation and evolution. The diversity of atmospheres is a testament not only to the vast variety of planetary systems, but also to the intricate factors that drive these variations. This exploration contributes to the growing field of astrobiology, offering essential insights that could help identify planets with conditions suitable for life. The case of TRES-2b also sheds light on the broader field of planetary science, pushing researchers to refine their models for predicting the atmospheric conditions of exoplanets. By understanding how extreme environments, such as those found on TRES-2b, shape a planet's atmosphere, scientists are better equipped to anticipate the habitability and environmental conditions of distant exoplanets. These findings play a critical role in advancing our search for life elsewhere in the universe, allowing us to better predict which exoplanets might harbor conditions conducive to life. The stark darkness of TRES-2b is, in many ways, a direct consequence of its extreme orbital environment. The planet's close orbit results in the absorption of immense stellar radiation, which heats the planet to blistering temperatures. This constant barrage of heat drives the vaporization of various elements and compounds, forming thick clouds of metallic compounds in the atmosphere. These clouds are highly efficient at absorbing light from the star, reinforcing TRES-2b's dark appearance and further diminishing its reflectivity. As such, TRES-2b offers an unparalleled example of how extreme thermal environments can give rise to unique planetary characteristics, an insight that helps researchers unlock the mysteries of distant worlds and the forces that shape them. Imagine a planet so close to its star that its entire surface is locked in a perpetual dance with the light. TRES-2b, a world located just a few hundred light years away, orbits its star in such a way that one side of the planet constantly faces the fiery glow, while the other side is plunged into unrelenting darkness. This phenomenon, known as tidal locking, results in an extraordinary climate, one that defies the boundaries of our understanding. On the sunlit side, Tier ES2b receives vast amounts of radiation, which superheats its atmosphere, driving intense and complex weather patterns. The relationship between the planet's orbit and its atmosphere is not merely a backdrop for dramatic weather. It's the key to understanding its extreme environment. The intense heat absorption on the day side leads to a feedback loop where atmospheric conditions amplify the planet's reflective qualities. What results is a climate where light and energy dynamics are governed by a delicate balance between heat, radiation, and the planet's position in space. In short, this orbit defines not only the temperature of the planet, but also its fundamental physical properties. TARES-2b stands as a testament to how a planet's proximity to its star can shape its atmosphere in ways that seem almost alien. With its close orbit, the planet's extreme characteristics stretch beyond the norm. If we were to observe the planet's surface, it would be hard to fathom anything like it in our own solar system. The extreme heat would be impossible to miss, with the surface reaching a staggering 1,150 degrees Celsius. This unrelenting heat would drive a variety of atmospheric phenomena. Powerful winds would likely sweep across the planet's surface as different parts of the atmosphere experience rapid heating and expansion. As these sections rise, they create zones of low pressure, leading to strong convective currents. These swirling air masses, driven by the intense radiation from the nearby star, would fuel fierce winds, creating a truly chaotic and unpredictable environment. Such weather would have profound effects on cloud formation and the planet's overall climate. These shifts in weather could happen on a dime, as the planet's atmosphere constantly struggles to maintain equilibrium. But the atmosphere of TARES-2b is not just a theater of extreme winds and temperature. The planet's air may contain metallic vapors, a direct result of the searing heat, and under the right conditions, they might condense into metallic droplets. These droplets could fall to the ground in a form of precipitation unlike anything we've ever experienced on Earth. Imagine liquid metals raining down from the sky, further emphasizing the extreme and alien nature of TARES-2b's climate. The planet's perpetual daylight on one side, contrasted with its unrelenting darkness on the other, creates even more atmospheric complexity. The side exposed to the star constantly experiences blistering heat, which destabilizes the air, leading to frequent upheavals and violent storms. Meanwhile, the dark side, perpetually shielded from the star's rays, cools down dramatically, with temperatures plummeting to extreme lows. The atmospheric circulation between these two wildly different regions is likely erratic and unpredictable, creating weather patterns that challenge our current understanding of meteorology. In sum, the atmospheric dynamics on TARES-2b are driven by extremes: intense heat, perpetual darkness, metallic vapors, and dramatic shifts between the day and night sides. These features combine to form an environment unlike any other in our known universe, one that not only piques our curiosity, but also offers a unique opportunity to learn about alien worlds. Life on TARES-2b, a battle against the darkness. But what about life on TARES-2b? Could anything survive on this blistering, shadowy world? The answer, while speculative, lies in the planet's extreme conditions. Without sunlight, one of the most fundamental ingredients for life as we know it, photosynthesis, the process by which plants and other organisms harness solar energy, would be impossible. The atmosphere of TARES-2b absorbs nearly all incoming light, casting its surface into a perpetual gloom. For life to thrive in such a hostile environment, it would need to find alternative ways to generate energy. One possibility is that life might tap into the geothermal energy of the planet's core, drawing heat from the deep interior. Alternatively, chemical energy derived from hydrothermal vents, should they exist on the planet's surface, could be another source. Extremophiles on Earth, organisms that thrive in environments such as deep-sea vents or highly acidic lakes, offer us a glimpse of what life on TARES-2b might look like. Yet, the life forms here would have to adapt in ways that go far beyond anything on Earth, evolving to withstand temperatures that would be lethal elsewhere. TARES-2b is a world that continuously challenges our understanding of the cosmos. Its intense heat, perpetual darkness, and unpredictable weather patterns are a reminder of how diverse and unexpected planetary environments can be. While life on Trias 2b may seem impossible, the planet's extreme conditions beckon us to reconsider what we know about life's potential, not just here on Earth, but across the universe. On a planet like Tres 2b, the thick, metallic-rich atmosphere poses not only a breathtaking view, but also a series of formidable challenges. High temperatures could transform the environment into an inhospitable furnace, where intense heat combines with a cocktail of corrosive chemicals. Life forms, if they exist in such extreme conditions, would have to evolve incredibly resilient mechanisms to endure. They would need protection from blistering temperatures and the hostile, tactile environment saturated with gaseous metals. The planet's dynamic weather, driven by its extreme heat and complex atmospheric composition, would introduce additional hazards. High-velocity winds and the potential for metallic droplets to precipitate would create a constantly shifting landscape, one that would be nearly impossible for any life forms to call home. These volatile conditions would make it nearly impossible for stable habitats to form, forcing organisms to adapt in ways we can barely imagine. The challenges are immense, but this also sparks curiosity. What kind of life could survive here? It's likely that any life forms would bear little resemblance to life on Earth, similar to how extremophiles thrive in Earth's most inhospitable corners. These potential beings would likely rely on alternative energy sources and possess radically different survival strategies, finely tuned to endure in a world of perpetual darkness and hostile forces. The very nature of exploration on such a planet presents a series of unique and daunting challenges. For one, the absence of natural light would severely hinder visibility, making conventional imaging and observation nearly impossible. Instruments relying on sunlight or other forms of light would struggle to provide the necessary data. Instead, advanced spacecraft would need specialized technology, like infrared sensors, to detect heat signatures from the planet. These sensors would reveal critical geological features that would otherwise remain hidden in total darkness, offering crucial insights into the planet's structure and history. Communication, too, becomes a significant hurdle. Without the advantage of light to carry signals, radio waves would take longer to travel, amplifying the delay in data transmission between the planet and Earth. This increased distance would complicate real-time monitoring and decision-making, a major concern for any space mission. Additionally, if the planet's atmosphere is dense or surrounded by debris, these factors could further interfere with communication efforts, adding layers of difficulty to the already complex task of studying such a distant world. Exploring the surface of Tres 2b presents yet another challenge. Rovers and landers would have to navigate rugged, shadowed terrain, a task that would require cutting-edge engineering and sophisticated navigation systems. With much of the planet's surface perpetually shrouded in darkness, any efforts to collect samples or analyze geological features would need to be adapted to the low-light conditions. Autonomous systems would likely play a crucial role, ensuring that operations could continue successfully without the need for constant human intervention. These systems would have to be robust, agile, and self-sufficient, capable of functioning in a hostile environment with little to no direct oversight. Ultimately, studying a planet like Tres 2b offers a fascinating glimpse into the unknown, sparking the imagination of scientists and explorers alike. Yet, it is clear that only through ingenuity and adaptability could humanity hope to overcome the many obstacles this dark, mysterious world presents. In understanding the environmental conditions of distant dark planets, researchers face an array of daunting challenges. Extreme temperatures, shifting atmospheric compositions, and unpredictable surface dynamics all play a part in making these worlds mysterious and hazardous to explore. For missions targeting such planets, developing robust protective measures for spacecraft is essential. These measures must withstand not only the bone-chilling cold of perpetual darkness, but also the crushing atmospheric pressures and volatile chemical compositions that may lie hidden within these alien atmospheres. The complexities of these environments underscore the ingenuity and precision required to successfully navigate and study such extreme worlds. One exoplanet that captures the imagination of astronomers is Corot 7b. This planet, located far beyond our solar system, stands out due to its extreme and challenging conditions. Korat 7b is classified as a hot super-Earth, meaning it is larger than our own planet but still smaller than Neptune. Its proximity to its host star results in an intensely hot surface, likely exceeding temperatures of 1,000 degrees Celsius. This searing heat forces the planet's surface minerals and rocks into a state of constant melting, creating a landscape akin to a vast, ever-churning ocean of molten lava. The conditions are so extreme that, in many ways, Korat 7b appears as though it is constantly on the verge of a fiery eruption. The planet's unique characteristics are further shaped by its tidal locking to its star. One side is perpetually facing the heat, while the other is plunged into unending darkness. This causes an extraordinary temperature gradient, with one half of the planet boiling under the sun's unrelenting rays, while the other remains frozen in eternal shadow. The result? A planet defined by both extremes, where lava oceans clash with frozen wastelands. This stark divide creates dynamic and ever-shifting atmospheric conditions, adding layers of complexity to any exploration of Korat 7b. The heat on the planet's sun-facing side is so intense that it fuels active volcanic activity. Gigantic lava flows surge across the surface, creating a landscape that is constantly reshaped by the forces of geology. Spectroscopic studies have confirmed the presence of silicate minerals, which are key to understanding the planet's volatile surface. These minerals, much like those found on Earth, melt and churn under the extreme temperatures, creating a fiery, molten landscape. The continuous volcanic activity and intense heat make Korat 7b a planet of blistering surface conditions, an ever-shifting molten world. Beyond its striking appearance, Korat 7b is an invaluable subject for scientific study. Researchers are particularly fascinated by the insights this planet can offer into the formation and evolution of rocky exoplanets. By studying the dynamics of Korat 7b's surface, scientists can learn more about the processes that shape other planets in distant solar systems, broadening our understanding of planetary formation far beyond our own corner of the universe. Korat 7b orbits its star at a distance that is shockingly close, approximately 3 times nearer than Mercury is to our Sun. This proximity exposes the planet to immense levels of stellar radiation and heat, pushing it to the edge of what is known as the habitable zone. A single orbit of Korat 7b around its star takes less than 1 Earth day, meaning the planet is constantly bombarded with thermal extremes. These scorching temperatures are the driving force behind the planet's molten surface, creating a spectacle of eternal geological activity. In essence, Korat 7b is a planet like no other, one that combines blistering heat, a molten surface, and extreme atmospheric conditions. Its study offers a glimpse into the potential diversity of exoplanets that exist in the far reaches of the cosmos, each more mysterious and wondrous than the last. Additionally, the gravitational pull between Korat 7b and its host star causes a dramatic tidal effect, leading to a phenomenon known as tidal locking. This forces one side of the exoplanet to remain in constant daylight, while the other side is perpetually cast into darkness. As a result, Korat 7b experiences an extraordinary temperature differential, one so extreme it shapes both its physical features and its atmospheric dynamics. These fluctuations in temperature aren't merely a curiosity, they are key factors that determine the planet's atmospheric potential. The intense heat on the sunlit side of the planet can soar to over 1,000 degrees Celsius, while the shadowed side cools to an almost freezing temperature, reaching as low as 0 degrees Celsius or even lower. The disparity between these two extremes is a consequence of the planet's permanent orientation toward its star, a result of tidal locking. On the daylight side, the planet's surface is relentlessly exposed to the star's intense energy, absorbing heat at a staggering rate. Meanwhile, the dark side remains cold and unaffected by this radiant energy. This leads to a constant battle of thermal equilibrium, driving extreme wind patterns and possibly fostering dynamic weather systems as heat attempts to redistribute itself across the planet's surface. This dramatic temperature variation holds vital clues about how exoplanets in extreme environments behave. The study of planets like Korat 7b enriches our understanding of planetary climates beyond our solar system. Not only does it deepen our insight into how temperature gradients can shape weather systems, but it also provides a window into the long-term viability of exoplanetary atmospheres. As temperatures swing from one extreme to another, the planet may struggle to retain its atmosphere, with lighter elements, such as hydrogen and helium, potentially being stripped away into space. At such high temperatures, the atmospheric composition of Corot 7b undergoes profound changes. The extreme heat is more than sufficient to cause the dissociation of lighter gases, which are among the first to escape into the vacuum of space. Without these essential components, Corot 7b may not possess a thick or stable atmosphere. The result is a world where the presence of lighter elements is scarce, while heavier molecules like silicates and metals, often present as vapor due to the high heat, begin to dominate the atmosphere. As minerals on the planet's surface melt, they release various compounds into the atmosphere, adding to its already complex composition. The low atmospheric pressure and density on Corot 7b are strikingly different from what we experience on Earth. While Earth's atmosphere can support life due to its relatively mild conditions, Corot 7b's atmosphere is tenuous at best, unable to sustain the same kind of protective shield that our own planet offers. In addition to these atmospheric challenges, the relentless heat causes dramatic atmospheric dynamics. The stark contrast between the blistering day side and the freezing night side generates powerful winds as the atmosphere tries to balance the thermal inequalities. These winds could contribute to dynamic weather systems, further shaping the planet's already volatile environment. However, the conditions on Corot 7b present a formidable barrier to human exploration. A spacecraft or a human attempting to land on this inhospitable world would face extraordinary challenges. The surface temperatures, which can exceed 1,000 degrees Celsius, would be enough to incinerate any unprotected object or individual. Current spacesuit technology is far from sufficient to protect a human from such extreme heat. Any spacecraft landing on Corot 7b would likely experience catastrophic damage, with components exposed to the intense thermal radiation being unable to withstand the scorching conditions. If a human or spacecraft managed to reach the planet's surface despite the extreme temperatures, the consequences would be immediate and devastating. The heat would ignite materials upon contact, causing rapid combustion. In addition to the danger to the body, the high temperatures would likely cause catastrophic failures in the spacecraft's systems, from navigation to communication, rendering any attempt at landing a near impossible mission. Corot 7b's extreme environment serves as a reminder of the complex and often unforgiving conditions that exist on planets outside our solar system. By studying these planets, we gain insight not only into their formation and evolution, but also into the potential for life in such harsh environments. However, for now, Corot 7b remains a world too hostile for human exploration, a testament to the fierce forces at play on distant exoplanets. Corot 7b, a distant exoplanet, presents a fascinating yet formidable landscape that challenges our understanding of planetary science and space exploration. Its extreme conditions provide both a cautionary tale and a glimpse into the forces that shape planets in the far reaches of our universe. One of the most critical factors in exploring Corot 7b is its potentially thin atmosphere, or lack thereof, which would pose a severe obstacle for any spacecraft attempting to land. The absence of an atmosphere means there is no air resistance to slow descent, making traditional landing profiles, which rely on aerodynamic forces, obsolete. Spacecraft that are designed to endure harsh environments would have to overcome this challenge, relying on advanced technologies and systems to survive. Robust thermal protection systems would be paramount in ensuring that spacecraft could withstand the intense heat during landing. Materials capable of enduring extreme temperatures for the duration of the landing and beyond would need to be incorporated. This would require more than just protection. Engineers would also have to guarantee that critical systems within the spacecraft remained operational under these severe conditions. Every step of the process, from entering Corot 7b's atmosphere, or lack thereof, to landing, would push the limits of modern technology. Once on the surface, however, the challenges would not end. Corot 7b's volcanic activity presents another major complication for surface operations. The planet is subject to internal stresses generated by the immense tidal forces exerted by its star. Being tidally locked, Corot 7b has one side perpetually facing the star and the other side forever in darkness. This constant gravitational interaction not only generates heat, but causes the planet's interior to stretch and flex, resulting in tidal heating. This process generates significant friction deep within the planet, further raising surface temperatures and contributing to a dynamic and potentially hazardous geological environment. As a result of tidal heating, Corot 7b's surface is likely to be dominated by volcanic activity. The heat generated from within the planet could lead to the melting of subsurface rocks, creating pockets of magma that could occasionally erupt, reshape the surface, and trigger lava flows. These eruptions, in turn, could alter the composition of the planet's atmosphere by releasing gases and materials into its thin, tenuous envelope. The planet's dynamic geology, however, is not limited to volcanic activity. The stark thermal contrast between the side facing the star and the side in perpetual darkness creates unique geological features along the terminator line, the boundary between day and night. Here, the interaction of extreme temperature differences could trigger distinctive weathering processes, possibly even leading to the formation of specialized structures that have never been seen elsewhere in the universe. These processes offer clues about how planets with extreme conditions evolve over time, providing valuable insights into the forces shaping planetary systems across the cosmos. The significance of these tidal forces extends beyond mere geology. The unique temperature distribution caused by tidal locking and the resulting geological processes shed light on the broader relationship between celestial mechanics and planetary evolution. The intense heat generated by tidal forces not only fuels volcanic activity, but also plays a crucial role in shaping Corot 7b's surface features. Understanding this interplay helps to deepen our knowledge of how planets in extreme environments evolve and how celestial bodies interact with their host stars in ways that are vital for their development. But Corot 7b's value lies not only in its geological activity. It also serves as a natural laboratory for understanding the processes of planetary formation and evolution. The extreme conditions found on lava planets like Corot 7b provide a unique perspective on the environments under which terrestrial planets form. These planets may have experienced similar heating in their early stages, driven by the proximity to their stars. By studying Corot 7b and planets like it, scientists can gain deeper insight into the role of stellar radiation and gravitational forces in planetary evolution. The molten surfaces and extreme temperatures observed on Corot 7b suggest that it underwent intense heating early in its history, likely due to its proximity to its host star. This intense heating, combined with tidal forces, may have played a significant role in shaping the planet's composition and surface features. Analyzing these conditions not only informs our understanding of lava planets, but also helps develop models of early planetary formation that can be applied to other rocky planets, including early Earth. By examining the extreme environments of lava planets, we learn about the materials available during planetary formation, the conditions under which they evolve, and how these planets develop based on their orbital characteristics and star types. The insights gained from studying Corot 7b could ultimately lead to advancements in our models of planetary formation, helping us understand the conditions that lead to the development of diverse planetary bodies in the universe. The study of lava planets, worlds where molten rock and extreme temperatures dominate the surface, opens a window into some of the most volatile and extreme conditions known to science. By examining how volatile elements and compounds behave on these planets, we can uncover insights into how materials are released or retained in high-energy environments. This knowledge is not only pivotal for understanding these extreme worlds, but also sheds light on more temperate planets that might share similar compositional traits. If such geological processes occurred elsewhere in the universe, they could help scientists assess the likelihood of discovering Earth-like planets capable of supporting life. Furthermore, studying lava planets challenges and broadens our definitions of habitability. These planets stretch the limits of what we consider livable, presenting planetary systems that are vastly different from our own. Yet, by pushing the boundaries of exploration into these extremes, we gain a broader understanding of planetary formation. This helps create a more nuanced view of the universe, one that highlights the remarkable diversity and complexity of worlds beyond our solar system. When it comes to investigating planets like Coro 7b, worlds with extreme surface conditions, the methods used are as innovative as the discoveries they lead to. One of the primary tools in this exploration is remote sensing, which allows scientists to study distant planets by analyzing the light they emit or reflect. Through spectroscopy, researchers can examine the spectrum of light interacting with a planet's surface and atmosphere. Each material has its own unique signature when it comes to absorbing and emitting light. And by identifying these wavelengths, scientists can glean crucial information about the planet's composition, including the presence of silicates, metals, and other chemical compounds. Even under the extreme heat of these lava worlds, infrared spectroscopy proves invaluable, as high temperatures cause certain materials to emit infrared radiation, allowing scientists to detect and study them from afar. This method is made possible by advanced telescopes and space observatories, which capture spectral data from these distant worlds. With this data, researchers can infer a planet's surface composition without the need for direct physical sampling. But spectroscopy isn't the only tool in the scientist's arsenal. Another technique involves analyzing the gravitational interaction between the planet and its host star. By observing how the planet's gravity affects its star, causing it to wobble, scientists can estimate the planet's mass and density. These factors give additional clues to the planet's makeup. A higher density might suggest a rocky or metallic core, while a lower density could indicate a more gaseous structure. In addition to these direct methods, scientists also turn to models of planetary formation, drawing upon theories about how planets evolve under extreme conditions. By combining observational data with these theoretical frameworks, a clearer and more complete picture of planets like Coro 7b begins to take shape, allowing researchers to piece together the planet's composition even under harsh and unyielding conditions. The view from the surface of Coro 7b would be nothing short of extraordinary. With one side of the planet always facing its star, the day side is subjected to constant and intense illumination. The sky would appear overwhelmingly bright, flooded with the star's harsh light. If an atmosphere is present, it could scatter this light, creating a blinding brilliance that would flood the landscape. The harsh glare on the day side would contrast sharply with the eternal darkness of the night side, where no sunlight ever touches. In this permanent night, the sky would be a stunning vista of stars, offering an unparalleled view of distant cosmic phenomena. It would be the ultimate stargazing experience, where the darkness of space reveals itself in all its beauty, unbroken by the interference of the sun. However, the extreme temperatures on the day side of Coro 7b might limit the potential for a thick atmosphere, leaving the sky thin and hazy. Such conditions would slightly diminish the visibility of the celestial body, but if volcanic or geological activity were present, the atmosphere could fill with ash and gas particles. This could create a vibrant, shifting canvas of colors during twilight, dramatically altering the skyline during the rare moments near the terminator line, the boundary between day and night. If Coro 7b's atmosphere were rich in gases released by volcanic processes, the sky could present an even more diverse array of hues. Depending on the composition of the atmosphere, one could witness greens, reds, and yellows streaking across the heavens. The experience of looking up from the surface of Coro 7b would be like nothing on Earth, with extreme brightness and dynamic atmospheric conditions painting a unique picture. This planetary landscape is shaped by the planet's peculiar orbit and relationship with its star, a dynamic that transforms each shift in position into a new, captivating perspective on the cosmos. As the planet undergoes these constant changes, the interplay of heat, light, and geological processes defines the landscape. Over time, Coro 7b is expected to undergo gradual yet profound transformations, driven by its close proximity to its host star and the ongoing evolution of planetary forces. Tidal forces, exerted by the gravitational pull between the planet and its star, are one of the primary contributors to Coro 7b's extreme conditions. These forces cause ongoing heating, which could influence the planet's geological activity. Initially, tidal heating may drive volcanic processes, shaping the planet's surface, but as the planet cools and loses its internal heat, the level of geological activity may decrease, potentially slowing or halting volcanic activity entirely. One of the most significant consequences of Coro 7b's exposure to intense stellar radiation is the potential loss of its atmosphere. If the planet possesses an atmosphere, constant exposure to this high-energy radiation could strip lighter elements away, especially those at the highest energy states. Over time, this atmospheric loss could lead to a thinning or even complete evaporation of the atmosphere. The result? A landscape increasingly exposed to the vacuum of space, with the rocky surface becoming more and more apparent. Ultimately, Coro 7b's future may be defined by an extended cooling phase as it exhausts its internal heat. With volcanic activity diminishing and the atmosphere thinning, the planet may transition to a more stable, cooler state. If the atmosphere dissipates entirely, Coro 7b could resemble other airless bodies in our solar system, such as the Moon or Mercury, whose barren, stark landscapes bear witness to the ravages of time. The extreme conditions shaping Coro 7b are thus likely to evolve from an active, molten world teeming with geological processes to a much more stable and cooler environment. This transformation underscores the fascinating, ever-changing nature of exoplanets and their potential evolution, offering profound insights into their life cycles across the cosmos. On the other hand, PSRB 1257 plus 12b, often called the zombie planet, exists in a far more extraordinary setting. This exoplanet orbits a pulsar, a highly magnetized, rotating neutron star that emits intense beams of radiation. Unlike typical planets that form around regular stars, PSRB 1257 plus 12b resides in a system where the host star has already met its violent end. Once a massive star, it exploded in a supernova, leaving behind only the dense, radiation-emitting core that now serves as the pulsar. The fact that a planet can exist in such a harsh environment long after the death of its parent star is what has earned PSRB 1257 plus 12b the nickname Zombie Planet. The survival of PSRB 1257 plus 12b raises intriguing questions about planetary formation and survival in extreme environments. When the pulsar formed from the collapse of its progenitor star, any material surrounding it would have been subjected to catastrophic levels of radiation and gravitational forces. Yet, PSRB 1257 plus 12b not only survived but continues to orbit the pulsar, suggesting that it may have formed earlier and was resilient enough to withstand the violent events that led to the creation of the pulsar. This resilience leads to a hypothesis that some planets could form from residual material left behind after a star's death, rather than solely from a circumstellar disk around a living star. PSRB 1257 plus 12b's existence challenges our understanding of planetary survival and formation, showing that planets can persist in environments previously thought to be uninhabitable, further deepening the mystery of planetary evolution in the universe. PSRB 1257 plus 12b orbits around a pulsar, a star that is vastly different from the ones we're familiar with. This means that the planet endures extreme conditions far beyond those on Earth or even many other exoplanets. The intense radiation it faces has the potential to drastically alter its atmosphere and surface. This harsh environment makes it incredibly unlikely for life as we know it to survive there, especially when compared to the more hospitable conditions of planets orbiting sun-like stars. In fact, the very existence of PSRB 1257 plus 12b challenges our understanding of planetary systems, prompting scientists to reconsider how planets can form, evolve, and persist, especially after the violent death of their host star. This zombie planet stands as a remarkable example of resilience in the universe, sparking further exploration into the vast diversity of planetary environments scattered across the cosmos. A pulsar is no ordinary star. It is a highly magnetized, rapidly rotating neutron star that emits beams of radiation from its magnetic poles. These pulsars are born from the remnants of massive stars that, having run out of nuclear fuel, undergo a supernova explosion. During this catastrophic event, the star's core collapses under its own gravity, compressing protons and electrons to form neutrons, creating an incredibly dense object. This collapse transforms the star into a neutron star, and if the conditions are just right, it can become a pulsar. What sets pulsars apart from regular stars is their behavior and physical properties. While a normal star, like our Sun, generates energy through nuclear fusion, turning hydrogen into helium and radiating light and heat, pulsars no longer undergo fusion. Instead, they rotate at incredibly high speeds, often several times per second or more, due to the conservation of angular momentum from the original star. The intense magnetic field and rapid rotation cause pulsars to emit beams of radiation that sweep across space like a lighthouse beam. When this radiation points toward Earth, we detect a pulse, creating the characteristic pulsing effect. Some pulsars are so precise in their emission that they serve as incredibly accurate cosmic clocks, allowing scientists to test theories of gravity and measure time across vast astronomical distances. In contrast, regular stars maintain a delicate balance between gravitational forces trying to collapse the star and the outward pressure from nuclear fusion. Pulsars, however, are the remnants of stars that have exhausted their fusion processes. They are characterized by rapid rotation, intense magnetism, and the emission of beams of radiation, all in a highly extreme and unstable physical state. The survival of PSRB 1257 plus 12b through the supernova that created its host pulsar is an extraordinary and puzzling event. When a pulsar is born, it marks the end of a massive star's life. The supernova explosion expels most of the star's outer material into space, creating a turbulent environment filled with high-energy radiation and powerful shockwaves. Yet against all odds, PSRB 1257 plus 12b managed to endure this cataclysmic event. One theory as to how this planet survived revolves around its formation and location. It's possible that PSRB 1257 plus 12b formed from residual material left behind in the protoplanetary disk that surrounded the progenitor star before it went supernova. This would suggest that the planet was embedded in material that was shielded from the brunt of the explosion, allowing it to remain intact. Another possibility is that the planet's survival is due to its distance from the progenitor star. If PSRB 1257 plus 12b was far enough away from the explosion, the energy released during the supernova might not have been enough to destroy or disrupt it. This distance would have enabled the planet to withstand the radiation and the ejected material typically associated with such catastrophic events. In any case, the survival of PSRB 1257 plus 12b highlights the complex and unpredictable nature of planetary systems, where even in the face of extraordinary destruction, resilience can emerge in the most unlikely of places. The planet's existence challenges traditional models of planetary formation and stability, showing us that the universe has far more surprises in store than we could ever have imagined. The dense conditions created by a supernova are more than just catastrophic. They may have played a pivotal role in shaping the orbit of the planet PSRB 1257 plus 12b around its host pulsar. As the outer layers of the progenitor star were expelled in the explosive event, the gravitational influence of the system shifted dramatically. If PSRB 1257 plus 12b was already in orbit at the time, it's conceivable that the dynamics of the explosion adjusted the planet's trajectory, allowing it to settle into a stable orbit around the newly formed pulsar. This suggests that the planet's survival, despite such a violent origin, speaks to the extraordinary resilience of planetary bodies. More than that, it unveils the complex nature of planetary systems, especially those born in the chaotic aftermath of stellar evolution. This unusual scenario raises fascinating questions about planetary formation, particularly in the tumultuous environments of dying stars. It challenges traditional understandings of planets can form and persist in cosmic conditions that seem utterly hostile to life. What does it take for a planet to endure in the shadow of a pulsar, a stellar remnant emitting intense radiation across vast distances? The case of PSRB 1257 plus 12b invites us to reconsider the range of possibilities for planetary survival and the robustness of celestial bodies in the face of extraordinary cosmic forces. PSRB 1257 plus 12b finds itself constantly bombarded by radiation, a consequence of its proximity to the pulsar that holds it in its gravitational grip. As a pulsar, PSRB 1257 plus 12 emits beams of electromagnetic radiation, spanning radio waves, X-rays, and gamma rays. This radiation results from the pulsar's rapid rotation and its powerful magnetic field, which accelerates charged particles to astonishingly high energies. As these particles travel along the pulsar's magnetic field lines, they create energetic emissions that can be detected across vast stretches of space. For a planet like PSRB 1257+12b, the intensity of this radiation is far greater than anything Earth experiences. The environment surrounding a pulsar is one of extreme conditions. Radiation levels are so intense that they could strip away a planet's atmosphere, rendering it inhospitable for life as we know it. The constant bombardment of energetic particles could alter the planet's surface, while the high-energy radiation could erode or vaporize its atmosphere, making it impossible to retain volatile elements like water or gases that are crucial for sustaining life. The radiation, in essence, would challenge any potential for habitability, making PSRB 1257+12b an unlikely candidate for harboring life forms, at least in the conventional sense. Beyond these challenges, the radiation itself could also influence the surface of the planet in profound ways. The intense energy from the pulsar can lead to significant surface heating, potentially stripping away the lighter atmospheric components. Over time, prolonged exposure to such severe radiation could erode any remaining atmosphere, further altering the planet's characteristics. This process would drastically change the planet's composition and possibly render it incapable of retaining the building blocks for life. In this way, the planet becomes a reminder of the extreme conditions found in the universe, where planets must contend with powerful forces that can reshape or even erase their existence. The high-energy environment surrounding pulsars provides a unique window into the violent processes of stellar evolution. It offers us a deeper understanding of planetary dynamics in the presence of such destructive forces, as well as the potential challenges planets face when caught in the orbit of a pulsar. Studying these extreme conditions not only sheds light on the unique environments of pulsar systems, but it also deepens our understanding of the broader universe and the kinds of conditions planets must endure to survive. The proximity of a planet to a pulsar influences its physical properties in remarkable ways. Pulsars emit highly energetic beams of electromagnetic radiation, which can dramatically affect any celestial bodies in their vicinity. For planets that orbit closely to a pulsar, the surface can experience extreme radiation levels, leading to intense heating and, in some cases, the stripping of their atmospheres. The strong gravitational and magnetic forces of a pulsar can also affect a planet's geological structure, potentially causing tectonic activity or altering the planet's surface composition in unpredictable ways. Additionally, the intense radiation emitted by the pulsar can produce awe-inspiring phenomena. For instance, the auroras generated by the charged particles interacting with the planet's magnetic field would dwarf anything seen on Earth, creating spectacular light shows of cosmic proportions. These auroras are a visible testament to the violent interaction between a planet and its host pulsar. However, the distance from the pulsar is a critical factor in determining a planet's potential for habitability. A planet too close to its pulsar will be subjected to lethal doses of radiation, rendering it uninhabitable. The extreme radiation environment would likely destroy any biological life forms and prevent the formation of stable atmospheres necessary for sustaining life. In conclusion, the study of planets like PSRB 1257+12b challenges our perceptions of what is possible in the universe. It provides a compelling case for the resilience of planetary bodies and offers critical insights into how planetary systems form and evolve under the extreme conditions created by dying stars. As we continue to explore the universe, these extreme environments remind us of the immense forces at play in the cosmos and the remarkable ability of planets to survive in the face of unimaginable challenges. However, if a planet orbits within a specific region known as the habitable zone, the conditions could, in theory, allow for some form of life to exist despite the overwhelming presence of pulsar radiation, provided that local protective mechanisms are in place. This habitable zone is a delicate balance, where the right distance from a pulsar might offer for just enough shielding to keep the planet viable for life. Interestingly, though, if a planet is positioned too closely to a pulsar, the relentless barrage of high-energy particles can begin to erode its atmosphere over time, rendering it barren and lifeless. Pulsars, while fascinating, often have the potential to strip away the very essence of a planet, with their powerful radiation slowly decimating atmospheric layers, leaving behind a desolate world. The characteristics of planets orbiting pulsars are largely shaped by their proximity to these enigmatic remnants of massive stars, making them a captivating subject for astrophysical research. Imagine standing on the surface of PSR B 1002-2257+12b, a planet orbiting a pulsar. The sky would be a striking, surreal spectacle, dominated by the pulsing light of the pulsar itself. This dense neutron star, the heart of the system, would glow fiercely in the heavens, casting its electromagnetic beams across the vast cosmos. Pulsars rotate with incredible speed, sending out beams of radiation in rhythmic pulses, much like the beams of a lighthouse. These beams sweep through space in an unbroken, constant rhythm, creating an effect that would seem almost otherworldly when viewed from a planetary surface, far from Earth's familiar sky. The intensity of the radiation emitted by the pulsar would likely result in a vibrant display of auroras in the planet's atmosphere, if it has one. These natural light shows, caused by high-energy particles colliding with atmospheric gases, could fill the sky with brilliant, almost ethereal colors, shades of green, blue, and red dancing through the atmosphere. The landscape would be dramatically different from Earth's, with the pulsar's unyielding energy shaping an environment both beautiful and perilous. This constant bombardment of radiation would make it an extremely hostile place, yet visually striking in ways no Earth-bound aurora could match. The other celestial bodies in the sky would only add to the dramatic scenery. Depending on the planet's position in relation to other stars, those stars might appear unusually bright and sharp, their light undistorted by any atmospheric pollution or distortion. If there are other planets in the system, their positions could offer fascinating views as well, adding to the intricate tapestry of light in the sky. Nightfall, however, might not bring the typical darkness we're accustomed to. The pulsar's constant radiation means the planet's nighttime could be bathed in a never-ending twilight, depending on the alignment of the pulsar's beams. Alternatively, the planet might experience sudden contrasts, shifting between bursts of intense light and sharp periods of shadow, creating a dynamic and unpredictable sky that is both mesmerizing and intimidating. In this environment, the regular pulses emitted by the pulsar profoundly shape the planet's climate, creating conditions that are at once fascinating and extreme. These pulses of radiation, emitted at precise intervals, have a continual, powerful impact on the planet's atmosphere. If the planet is close enough or has a thin atmosphere, the intense energy could ionize the gases that make up the atmosphere, triggering unusual chemical reactions. This ionization process could gradually strip away the atmosphere entirely, leaving the planet exposed to the full brunt of the pulsar's radiation. If this happens, any water or organic compounds that might exist on the planet's surface could either evaporate into space or break down into simpler, less complex molecules. The relentless, periodic nature of the pulsar's beams creates another fascinating and extreme aspect of the planet's environment: temperature fluctuations. When the pulsar's radiation is directed at the planet, temperatures could soar, causing the surface to heat up dramatically. However, during those intervals when the beams are not aligned with the planet, the temperature could drop significantly, creating a cycle of intense, almost unlivable extremes. These rapid changes in temperature could result in dynamic weather patterns that contrast sharply with the stable conditions we see on Earth. The planet would experience a volatile, ever-changing environment, one that is both captivating and unforgiving. Imagine a world far from Earth, where the very essence of survival is dictated by the harshest of cosmic forces. In the case of PSR B 2157+12b, a planet orbiting a pulsar, the relentless bombardment of radiation provides a constant and vivid spectacle. As charged particles emitted by the pulsar collide with the planet's magnetic field, they trigger breathtaking auroral displays. These radiant light shows are not mere visual phenomena. They carry profound consequences for the planet's atmosphere, potentially altering it in ways we are only beginning to understand. The regular pulses of radiation from the pulsar create a distinct environment that challenges both our imagination and the very foundations of planetary science. PSR B1257 plus 12b is one of the first extrasolar planets discovered orbiting a pulsar. It serves as a vital case study, defying traditional ideas about planet formation. Typically, planets form in the warm, stable conditions around stars, but this world exists under a much more extreme scenario. The intense radiation from the pulsar suggests that planetary bodies might not only form around ordinary stars, but also thrive in radically different environments. The radiation environment around the pulsar demands a radical rethinking of how we understand planetary atmospheres and surfaces. If PSR B257 plus 12b does indeed have an atmosphere, it is remarkable to think about how this atmosphere has managed to persist despite the constant onslaught of pulsar radiation. Understanding how such an atmosphere might be sustained could offer crucial insights into the mechanisms that allow planets to maintain their atmospheric integrity even in hostile environments. This has profound implications for the search for life in the universe, challenging our established theories about what conditions are necessary for habitability. Moreover, the survival of PSR B1257 plus 12b over billions of years offers a fascinating glimpse into planetary resilience. The bombardment by pulsar radiation, far more intense than anything Earth experiences, pushes the limits of what planetary materials can withstand. By studying how the composition of the planet has been altered by radiation and particle influx, scientists can unlock new information about the processes that determine the longevity and stability of planets subjected to extreme conditions. Geological features and surface compositions on such planets provide critical clues about their evolutionary histories. PSR B1257 plus 12b, with its unique set of challenges, reveals how planets in hostile environments evolve in ways very different from those in more temperate regions of space. The planet's very survival serves as a testament to the adaptability of nature, offering clues about the possibility of life, or at least lifelike processes, existing in places once thought inhospitable. This study also sheds light on the broader dynamics of planetary systems formed around unusual stellar remnants like pulsars. These systems offer a different view of how planets are born and maintained, expanding our understanding of the immense variety of formation processes across the universe. PSR B1257 plus 12b highlights just how diverse these processes can be, offering insights not just into our own solar system, but into the broader cosmic landscape. To uncover the secrets of planets like PSR B1257 plus 12b, scientists use an array of advanced techniques. Pulsar timing, for example, takes advantage of the remarkable precision with which pulsars emit their radiation. These cosmic clocks emit radio waves with incredible regularity. When a planet orbits a pulsar, its gravitational influence causes tiny but detectable variations in the timing of these pulses. By analyzing these subtle shifts, astronomers can infer the planet's presence, its mass, and its orbital characteristics. Another tool at their disposal is the Doppler effect. As the planet orbits the pulsar, its gravity causes the pulsar to wobble, slightly altering the frequency of the radiation it emits. This wobble provides crucial data about the planet's mass and its orbital shape. Highly sensitive radio telescopes are essential to detecting these faint signals and making these observations possible. In addition to these methods, scientists also rely on the transit technique. If the planet passes in front of the pulsar from our perspective, it can briefly block some of the pulsar's radiation, causing a temporary dip in brightness. This phenomenon helps confirm the planet's existence and provides further information about its size and orbital path. By combining results from these varied observational techniques, researchers can construct a detailed profile of planetary systems around pulsars. Each technique, whether it's timing, frequency analysis, or brightness variations, adds another layer of insight into the dynamics of these extreme environments. The goal is to understand how common such planets are and what characteristics define them, which in turn offers profound insights into the mechanisms governing planetary formation and evolution in such unusual settings. If life could ever exist on PSR B1257 plus 12b, it would need to evolve some extraordinary adaptations to cope with the extreme radiation emitted by the pulsar. One possible adaptation might be the development of highly efficient protective structures. Think of thick exoskeletons or shells that shield organisms from the harmful effects of radiation. Similar to the extremophiles on Earth, organisms on this planet might evolve biochemical pathways capable of repairing radiation-induced damage, allowing cells to continue functioning in the face of high levels of ionizing radiation. Ultimately, PSR B1257 plus 12b isn't just a distant world of scientific curiosity. It is a living laboratory, a natural experiment that challenges our understanding of the cosmos and the very nature of life. Its existence forces us to rethink what is possible in the universe, expanding the boundaries of habitability, resilience, and adaptation. In the vast expanse of space, strange and resilient worlds like this may hold the key to unlocking the mysteries of planetary formation and perhaps even the secrets of life itself. On PSRB 1257 plus 12b, the potential for life hinges on remarkable adaptations to extreme conditions, primarily driven by the relentless radiation of its pulsar. Organisms in this hostile environment may have evolved unique metabolic processes that thrive on radiation as a primary energy source, much like photosynthesis, but fine-tuned to harness the specific wavelengths emitted by the pulsar itself. This radiation-driven form of energy capture would allow life forms to survive in an environment that would be otherwise uninhabitable for most organisms. Such organisms would need to possess extraordinary resilience, adapting rapidly to fluctuating environmental conditions caused by the pulsar's relentless radiation. In fact, these life forms may have evolved the ability to reproduce at extraordinary speeds, alongside mechanisms for swift genetic mutation. This adaptability would be crucial for survival, ensuring that organisms can quickly evolve to cope with the rapidly changing and often hostile conditions around them. Through this accelerated evolutionary process, life on PSRB 1257 plus 12b could continuously find new ways to thrive in the shadow of the pulsar's intense radiation. In addition to rapid evolution, life may have found refuge below the surface of the planet, seeking protection from the direct bombardment of radiation. Subterranean environments, shielded from the harshest effects of the pulsar's rays, would offer stability and protection, allowing life to flourish in an environment that is otherwise erratic and dangerous. These underground habitats could provide a relatively stable environment for organisms, fostering their growth and survival away from the deadly radiation above. If life were to exist on PSRB 1257 plus 12b, it would likely showcase a range of remarkable biological innovations. These adaptations, ranging from radiation-harnessing metabolic processes to rapid evolutionary strategies and subterranean refuges, would be essential for survival in a landscape defined by extreme conditions and unpredictable fluctuations in radiation. Life on this planet would undoubtedly be a testament to nature's ability to adapt to even the harshest of environments. On another front, the distant exoplanet Gliese 1214b offers a different kind of mystery. This planet, located in the constellation Virgo, has sparked interest among scientists for its potential to harbor a vast global ocean. As a sub-Neptune-sized planet, it sits between Earth and Neptune in terms of size, boasting a radius that could allow for a significant amount of water, potentially existing in liquid form. Its size, density, and atmospheric composition suggest that Gliese 124b could have enough water to support an oceanic environment, especially given its equilibrium temperature, which likely allows for liquid water to persist on its surface. The planet's relatively low density further supports this hypothesis. When compared to other rocky exoplanets, Gliese 1214b's lower density suggests it is not composed largely of heavy metals or silicate materials. Instead, much of its mass is likely made up of lighter elements, potentially including vast quantities of water. Models of planetary formation suggest that planets in this size range, especially those within the habitable zone of their stars, are capable of retaining substantial amounts of water, further reinforcing the idea of a global ocean. Recent observations of Gliese 1214b's atmosphere have bolstered this theory. Through transit observations, scientists have detected water vapor in the planet's atmosphere, adding weight to the speculation that beneath the thick atmosphere, a global ocean might lie. The spectral signatures captured from these observations strongly suggest that that water plays a significant role in the planet's makeup, offering further support for the hypothesis of an oceanic world. Taken together, the potential for a global ocean on Glia 12-4b, combined with its favorable conditions for liquid water, paints a picture of a planet with the capacity to support life, one where oceans may stretch across the surface, possibly harboring alien ecosystems beneath the waves. This distant world presents a fascinating opportunity to explore the possibilities of extraterrestrial life in an environment radically different from our own, yet with echoes of Earth's own watery depths. The planet Gliese 12-4b holds exciting potential in the search for habitable worlds, as it seems to reside within its star's temperate zone, offering the possibility of liquid water. Its distance from its host star places it in a region where temperatures may be just right to support oceans, which could in turn harbor an ecosystem beneath the surface. These subtle clues suggest the intriguing possibility that Gliese 12-4b is engulfed by a vast global ocean, making it a prime candidate for further investigation in the quest for planets that could support life. However, the atmosphere of Gliese 12-4b is markedly different from that of Earth in several key ways. One of the most striking differences is the significantly higher concentration of water vapor. While Earth's atmosphere contains only a modest amount of water vapor, Gliese 12-4b's atmosphere is thought to be saturated with it, hinting at the possibility of an ocean hidden beneath the clouds. Alongside this, the planet's atmosphere is expected to be rich in hydrogen and helium, light gases that are far more abundant than the nitrogen and oxygen we find on Earth. These gases are typical of sub-Neptune-sized planets, and their prevalence here suggests a thicker, more expansive atmosphere on Gliese 12-4b, potentially influencing its climate and weather patterns in ways that differ sharply from those on Earth. In contrast to Earth's oxygen-rich atmosphere, Gliese 12-4b lacks certain gases like carbon dioxide and atmospheric oxygen in notable quantities. Earth's atmosphere supports a complex system of life forms that continuously recycle gases, a dynamic that seems to be absent on Gliese 12-4b. This may indicate that the planet's atmosphere is shaped more by its close proximity to its star and its unique formation history, possibly giving rise to chemical processes quite different from those occurring on Earth. This discrepancy could have significant implications for the planet's habitability, as the types of chemical reactions and conditions that might support life could vary drastically. The differences in atmospheric pressure and temperature also add layers of complexity. Gliese 12-4b's atmosphere is expected to have a much higher pressure than Earth's due to its thicker composition. This could affect the behavior of gases and influence critical processes like cloud formation and weather systems. These variances in composition, pressure, and temperature not only make for a fascinating comparison to Earth, but they also deepen our understanding of the broad diversity of planetary atmospheres in the universe. At the depths of Gliese 12-4b's potential ocean, the pressure would be far greater than anything experienced on Earth. The immense pressure comes from the weight of the water above, and it increases with depth. Given that Gliese 12-4b is classified as a sub-Neptune planet, it is hypothesized to possess both a thick atmosphere and a profound ocean, leading to significant hydrostatic pressure. To put this into perspective, Earth's oceanic pressure increases by approximately 1 atmosphere for every 10 meters of depth. On Gliese 12-4b, estimates suggest that its ocean could be several hundred kilometers deep based on its size and possible water content. If the ocean on Gliese 12-144b reaches depths of around 100 kilometers, the pressure at the bottom could be incredibly high, potentially reaching 10,000 atmospheres or more. Such extreme pressure would create an environment that could challenge our understanding of the behavior of water and the potential for life at such depths. Life forms, if they exist in these conditions, would need extraordinary adaptations to survive the immense pressure, as the physical and chemical properties of water would behave in ways vastly different from what we are familiar with on Earth's surface. The extreme environments of Gliese 12-4b's ocean depths would not only challenge our assumptions about life in hostile conditions, but also offer crucial insights into the potential for life in high-pressure aquatic environments throughout the universe. With a surface temperature that can range from 50 to 100 degrees Celsius, depending on its distance from its host star and the characteristics of its atmosphere, Gliese 12.4b's equilibrium temperature is conducive to keeping water in a liquid state. This further strengthens the idea that the planet could harbor a deep, potentially life-supporting ocean. Whether or not it can sustain life remains unknown, but the possibilities for future exploration and research are vast. However, the state of water varies dramatically with depth, influenced by the complex interplay of pressure and temperature. At shallow depths near the ocean's surface, where temperatures often remain close to equilibrium, water would likely remain in its liquid form. As one descends further into the ocean's depths, however, the situation changes. The temperature steadily increases due to the geothermal gradient, the natural rise in temperature with depth inside a planet. This combination of rising temperature and increasing pressure gives rise to several states of water under these extreme conditions. In the middle depths of the ocean, water could remain liquid despite significant pressure. This pressure increases the boiling point, allowing water to stay liquid at temperatures that would normally turn it to vapor. At depths of several kilometers, the conditions become even more extreme, and water can remain in a stable liquid form despite high temperatures, thanks to this immense pressure. But beyond these depths, where pressure exceeds a critical threshold, water undergoes an extraordinary transformation into a supercritical state. In this phase, water exists in a unique condition where the usual distinctions between liquid and gas blur. It behaves neither entirely like liquid water nor like steam, exhibiting properties of both, a phenomenon that could have profound implications on chemical reactions and life processes in that environment. On planets like Gliese 12.4b, at shallower depths, water might still exist in its liquid state. However, in the deeper regions, it could shift into a supercritical phase, where the balance between temperature and pressure defines the water's unique behavior. The interplay between these variables presents an intriguing challenge for scientists exploring the potential for life on alien ocean worlds. In an entirely water-covered planet, the absence of land would create unique weather patterns driven by the constant interaction between the ocean and the atmosphere. Without land masses to disrupt airflow, moisture would circulate continuously, leading to a more uniform and continuous atmospheric system. One key result could be near constant cloud cover, which, combined with high humidity, would lead to the formation of dense cloud systems, limiting the amount of sunlight that reaches the surface. This could create a dim, diffuse lighting effect that would alter the surface environment in ways we might not fully comprehend yet. The vastness of such an ocean could also foster powerful storms, with warm water serving as an energy source for atmospheric disturbances. In warmer regions, thunderstorms might be common, fueled by high evaporation rates and significant humidity. Under the right atmospheric conditions, tornado-like systems might develop over the warm water, creating localized, intense weather phenomena. These storms could unleash extreme weather conditions, including violent rainfall and powerful winds, contributing to a dynamic, ever-changing climate. In addition to these atmospheric disturbances, a planet entirely covered by water might experience unusual thermal stratification. Without terrain to introduce variability, the ocean's upper layers could heat up during the day, while the deeper layers remained cooler. This temperature gradient could give rise to ocean currents that interact with the atmosphere, generating large waves and choppy conditions that reflect changes in wind patterns above. There is also the intriguing possibility that bioluminescent organisms in the water could produce spectacular light displays at night. After a storm or disturbance, the water could light up in dazzling, intricate patterns, creating a mesmerizing effect across the ocean's surface. On such a planet, where water governs everything, the interaction between the ocean and atmosphere would result in an environment that is both extraordinary and complex, constantly shifting and evolving. Gliese 12.4b, a sub-Neptune exoplanet, offers an interesting case study. Significantly larger and more massive than Earth, it has a radius about 2.5 times that of our planet, and its mass is roughly 7 times greater. This massive size has important implications for its gravity, which would create a much heavier environment for any human visitors. The stronger gravitational pull would make walking or moving around considerably more difficult. A visitor to Gliese 12 Fort B would feel much heavier, experiencing acceleration due to gravity several times that of Earth's. This added weight would make normal activities like standing or walking more strenuous, leading to quicker fatigue. Over time, the body would need to adapt to these new demands, potentially affecting muscle strength and cardiovascular health. Furthermore, the increased size and mass of Gliese 12 Fort BB likely mean it has a denser atmosphere compared to Earth. The atmospheric pressure would be significantly higher, depending on the thickness of the atmosphere and the depth of the ocean. If this planet indeed has a global ocean, the higher atmospheric pressure would create complications for breathing, requiring specialized equipment or adaptations for survival. Temperature and atmospheric composition would also be crucial for any human visiting Gliese 12 Fort B. The environmental conditions could vary dramatically, from warm and humid to extreme weather patterns. Visitors would need to be prepared for fluctuating temperatures and conditions, possibly requiring advanced technologies or specialized gear to endure the challenges of this alien environment. While the exploration of Gliese 12 Fort B holds thrilling potential, the massive differences in size, mass, and gravity would present significant challenges for human exploration. The planet would require careful planning, research, and technological adaptation to ensure safe exploration. Studying Gliese 12 Fort B provides vital insights into the potential of water-rich planets across the universe. As one of the first discovered sub-Neptune-type exoplanets, Gliese 12 Fort B's characteristics challenge our traditional views of planetary formation. The presence of substantial water vapor in its atmosphere and the possibility of a global ocean beneath its surface raise intriguing questions about the conditions needed for liquid water to exist on other planets. The planet's size and mass suggest that it could retain a thick atmosphere rich in volatile compounds, including water, which challenges previous theories about planetary formation. This opens up the possibility that planets of similar size to Gliese 12 Fort B may accumulate significant amounts of water during their formation process. Observations of this planet encourage researchers to think beyond Earth-like worlds, expanding our understanding of the vast diversity of planetary types that could exist in the universe. The discovery of Gliese 12 Fort B may mark just the beginning of an era of exploration that will reshape our perception of planets and their potential for supporting life. The study of Gliese 12 Fort B offers scientists an exceptional opportunity to explore the processes that govern the retention of water in atmospheres on exoplanets. By understanding how this water-rich planet behaves under the influence of its host star, researchers can gain valuable insights into the dynamics of climate systems on similar planets. Specifically, how factors such as stellar radiation and atmospheric composition can shape diverse environmental conditions. The study of Gliese 12 Fort B also contributes to our growing understanding of habitability, as water is often considered an essential prerequisite for life as we know it. This makes the planet a significant target in the search for extraterrestrial life. Through the analysis of its atmospheric composition and environmental conditions, scientists can refine the criteria used to identify planets that may support life. This research places Gliese 12 Fort B at the forefront of our exploration into water-rich exoplanets, serving as a critical benchmark in our quest to understand the existence and characteristics of similar worlds scattered across the cosmos. As such, it lays the groundwork for future explorations and discoveries. However, Gliese 12 Fort B presents unique challenges for life, particularly due to the complete absence of land. A planet entirely covered by water would lead to an aquatic world, where ecosystems and evolutionary pathways would be shaped in ways we can only imagine. Without terrestrial landscapes, life forms on Gliese 12 Fort B would need to adapt to a predominantly water-based environment, evolving in ways that differ dramatically from the organisms we see on Earth. This ocean-covered world could foster a rich variety of marine organisms. Over time, species may develop specialized adaptations to thrive in the aquatic realm. Locomotion, feeding strategies, and reproductive mechanisms would likely be centered around the vast oceanic environment, with life forms relying on ocean currents and tides for the distribution of nutrients and energy. This could lead to complex food webs that function entirely within the aquatic domain, rather than following the land-based ecosystems we are familiar with. The absence of land also introduces new challenges for the distribution of essential nutrients. Without soil or rock to provide minerals, organisms would have to find alternative ways to obtain the resources necessary for survival. In this water-only world, life might evolve to harness nutrients directly from the ocean itself, creating an interconnected aquatic ecosystem powered by the dynamic forces of the sea. Such adaptations could lead to the emergence of entirely new biological processes that are radically different from anything found on Earth. In addition to the absence of land, the planet's vast oceans would introduce pressures and environmental conditions that could have a significant impact on life. With no terrestrial land masses to interrupt the flow of ocean currents, the planet's vast waters would be subject to constant temperature fluctuations and pressure changes. These variations would create distinct ecological niches, where organisms might have to adapt to survive at different depths, from the sunlit surface to the dark, crushing depths of the ocean. Some life forms might develop bioluminescence to survive in the pitch-black depths, using light as a tool for communication, navigation, or predation. Others might rely on unique methods of energy production, taking advantage of underwater volcanic vents or the chemical processes that occur in the absence of sunlight. These adaptations would open the door to a completely new realm of biological possibilities. Evolution on Gliese 12 Fort B would also differ drastically from life on Earth. On our planet, the development of complex land-based organisms is influenced by factors like gravity, resource competition, and environmental variability. On a water-only world, life would likely follow a different evolutionary trajectory, with simpler organisms evolving in response to the unique pressures of an aquatic environment. In the absence of land-based biodiversity, these ecosystems could be dominated by entirely new forms of life, adapted to the challenges and opportunities of life under the ocean. From the surface of Gliese 12 Fort B, the sky would present an entirely new and awe-inspiring sight. With no mountains, forests, or landforms to interrupt the view, the planet's horizon would consist of a smooth, continuous curve where the ocean meets the sky. The atmosphere, likely thicker than Earth's and rich in water vapor, would produce a constantly shifting and variable sky. Cloud cover might be dense, limiting direct sunlight, and the colors of the sky could shift throughout the day. At times, soft blues, greens, and yellows could dominate, giving the sky a shimmering oceanic hue rather than the crisp clarity we associate with Earth's atmosphere. This atmospheric scattering would bathe the planet's surface in a dim, diffused light, creating an otherworldly glow. On overcast days, the sky could appear uniformly gray, with clouds shifting and swirling in response to the planet's dynamic weather patterns, influenced by the warmth of the ocean below. These dramatic skies would serve as a constant reminder of the powerful forces at play in shaping the climate of this water-rich world. Without any landforms to break the view, the horizon would be uninterrupted, offering a serene yet surreal visual experience. The gradual blending of ocean and sky at the distant horizon could stir a sense of curiosity, inviting the observer to ponder what lies beyond the visible world. As the planet's waters shift and move, bioluminescent organisms might occasionally light up the ocean's surface, creating stunning displays of light in the otherwise dark expanse. These natural phenomena would add an extra layer of beauty to the already mesmerizing environment. In conclusion, Gliese 12 Fort B offers a unique window into the potential for life and ecosystems on a water-covered world. Its study not only deepens our understanding of how planets can retain water and develop climates, but also challenges our assumptions about the forms life might take on worlds unlike our own. The planet's distinct features, its aquatic nature, its dynamic sky, and its unique evolutionary possibilities make it an unparalleled object of study in the search for life beyond Earth. Additionally, if Gliese 12 Fort B were positioned closer to its host star, it could offer breathtaking sunrises and sunsets. Imagine vivid, dynamic colors splashing across the sky, painting it for mere moments. A stunning, ever-changing spectacle that would make each day feel like a unique visual event. The horizon from Glia 124b would, without a doubt, weave a mesmerizing tapestry, creating a truly exotic and otherworldly atmosphere for any potential explorers. This planet, entirely covered in water, presents an especially fascinating challenge to scientists. The mysteries of such a world require an intricate approach, combining advanced technology, remote sensing techniques, and theoretical models. One of the primary methods for studying this enigmatic world is sending spacecraft equipped with cutting-edge instruments. These tools allow researchers to gather data from afar, measuring a variety of planetary characteristics, such as the planet's gravitational field, magnetic field, and thermal emissions. Such data can offer invaluable insights into the planet's internal structure, revealing hidden secrets beneath its surface. For example, fluctuations in the gravitational field might suggest changes in the planet's density, hinting at the presence of solid land masses or varying depths of water. Additionally, by studying the light reflected off the planet's surface, scientists can deduce the materials that make up the planet, including possible organic compounds or minerals, especially with the help of infrared spectroscopy. This technique targets specific light wavelengths corresponding to various chemical compounds, making it an essential tool for identifying organic molecules in the water and potentially on the ocean floor. To further understand these aquatic worlds, scientists turn to computer simulations and theoretical modeling. These models help predict and visualize the conditions on planets entirely covered by oceans. By drawing data from similar bodies within our solar system, such as Europa, one of Jupiter's moons believed to harbor a subsurface ocean, researchers can study the effects of tectonic activity, ocean currents, and even atmospheric dynamics on such planets. When compared with data collected through space missions, these models offer a clearer picture of oceanic worlds, refining our understanding of their formation, composition, and potential habitability. For worlds like Europa, where submersibles or autonomous underwater vehicles are used to explore its hidden oceans, the same methods of remote sensing and modeling are applied, even as we venture into planets far beyond our immediate reach. By piecing together all these insights, scientists are slowly uncovering the puzzle of these mysterious water-covered planets. Gliese 400136b, known as the Ice on Fire planet, is another remarkable example of extreme planetary conditions. Discovered in 2007, this exoplanet is classified as a hot Neptune, a planet similar to Neptune in structure but orbiting dangerously close to its host star. This close proximity subjects Gliese 400136b to scorching heat, giving rise to remarkable physical and chemical phenomena. The term ice on fire aptly describes its composition, which likely contains a significant amount of water ice, even amidst the extreme temperatures on its surface. However, on the distant exoplanet Gliese 436b, water undergoes a radical transformation. Under the crushing pressures and searing heat, reaching over 700 degrees Fahrenheit, water is no longer the familiar solid ice we know on Earth. Instead, it shifts into a remarkable state known as a supercritical fluid. In this state, water exhibits a blend of both liquid and gas characteristics, a bizarre hybrid that defies our typical understanding of how water behaves. At such extreme temperatures and pressures, water molecules are compressed so tightly that they resist becoming gas, despite the intense heat. The water remains in a fluid state, but with properties more akin to a dense, supercharged liquid. It is in this paradoxical condition that water on Gliese 436b appears to be burning, despite the fact that it is still technically in a fluid state. Even more intriguing is the planet's atmosphere, which is believed to be composed of elements like hydrogen, helium, and heavier compounds. The combination of high temperatures and immense pressure creates a dynamic environment where complex chemical reactions are more likely, possibly even giving rise to entirely new atmospheric phenomena. In such an extreme setting, scientists have a unique opportunity to study how materials behave under conditions that push the limits of what we know. This strange phenomenon, often referred to as hot ice, reveals an astonishing aspect of Gliese 436b, a planet so alien in its nature that it stretches our imagination. Hot ice is the term used to describe water that exists not as solid or liquid, but as a supercritical fluid, a state where the boundaries between liquid and gas blur. On Earth, we think of ice as the solid form of water, but the conditions on Gliese 436b make that concept obsolete. Temperatures soar above 700 degrees Fahrenheit, and with the planet's proximity to its star, the pressure is overwhelming, far greater than anything we experience on Earth. This extraordinary pressure causes the water molecules to crowd together tightly, inhibiting their transition into gas. Instead of vaporizing, the water remains in a fluid state, but one that behaves like neither a liquid nor a gas. Known as supercritical water, it is a fascinating state of matter, one that can dissolve substances like a liquid and diffuse through materials like a gas. It is in this highly compressed and heated environment that hot ice can exist, where water retains a solid-like structure under conditions that would melt it on Earth. The study of this extreme behavior of water on Gliese 436b opens doors to exploring how other materials might react under similar conditions. It offers a tantalizing glimpse into how matter behaves on planets vastly different from our own. The implications extend beyond this exoplanet, suggesting that there may be other celestial bodies out there with environments that could similarly alter the fundamental properties of common substances. One of the defining features of Gliese 436b is its extreme surface pressure. This hot Neptune orbits its star at a dangerously close distance, resulting in a relentless combination of high temperatures and immense gravitational forces. The pressure on the planet's surface is far beyond what we experience on Earth, so high, in fact, that it alters the very behavior of water. On Earth, water transitions between solid, liquid, and gas depending on temperature and pressure. But on Gliese 436b, the staggering pressures prevent water from freezing into solid ice or vaporizing into gas. Instead, the interactions between water molecules are reshaped, allowing them to exist primarily in a dense supercritical state. In this supercritical state, water behaves like a liquid in some ways, able to dissolve and flow, but without the clear distinctions between liquid and gas that we see on Earth. The molecules are so tightly packed together that even at extreme temperatures, water does not evaporate. This stability allows for the existence of hot ice, water that remains fluid at high temperatures, yet retains an ice-like consistency, all due to the unique conditions of the planet. Gliese 436b's extreme environment, marked by high temperatures, immense pressure, and a distinctive atmosphere, makes it a rare and fascinating laboratory for studying the behaviors of water and other compounds. This knowledge not only deepens our understanding of this far-off world, but also expands our view of the incredible diversity of planetary systems across the universe. The study of Gliese 436b invites us to rethink the boundaries of possibility, showing us that the universe is full of strange and captivating phenomena waiting to be discovered. The intense pressure on Gliese 436b exerts a profound influence on the chemical reactions and interactions occurring within its waters, triggering complex phenomena not observed under standard atmospheric conditions. For example, the dissolved gases and minerals in the water might initiate intricate chemical processes, which in turn could affect both the atmospheric composition and the planet's geological activity. The combination of extreme pressure and temperature results in a highly fascinating and intricate state of water, one that compels scientists to delve deeper into understanding how such extreme conditions shape molecular behavior and influence the physical properties of substances across different planetary environments. However, the prospect of landing on Gliese 436b presents insurmountable challenges for both humans and spacecraft. As a hot Neptune, Gliese 436b is characterized by incredibly high temperatures that soar beyond 700 degrees Fahrenheit, coupled with immense atmospheric pressure far surpassing anything encountered on Earth. These two factors alone create an environment that is incompatible with human survival and the functionality of traditional spacecraft. For a human attempting to land on Gliese 436b, the immediate threats would be the overwhelming heat and pressure. The temperatures would far exceed the tolerable limits for human beings, leading to severe heat-related injuries or death within minutes. Humans require a stable, breathable atmosphere to survive, But Glia 436b's atmosphere, likely rich in hydrogen and other gases, would not provide the necessary conditions for respiration. Similarly, spacecraft designed for Earth or even other celestial bodies would face catastrophic failure upon entering Glia 436b's atmosphere. The intense heat generated during descent would demand advanced thermal shielding, beyond anything currently available, to prevent the spacecraft from burning up or disintegrating. Moreover, the enormous atmospheric pressure on Glia 436b could crush most conventional spacecraft, rendering them incapable of surviving the descent. Even if a spacecraft could be engineered to withstand the heat and pressure, the planet's surface is presumed to be a thick, gaseous atmosphere rich in supercritical fluids, not a solid surface. As such, any attempt to land on the planet would not be a traditional landing, as on a rocky or terrestrial body. Instead, the spacecraft would likely sink into a dense medium, much like a liquid, making standard landing protocols completely ineffective. These extreme conditions, the overwhelming temperatures, crushing atmospheric pressure, and the gaseous or supercritical nature of the surface, present insurmountable barriers to human exploration and traditional spacecraft landings. Glia 436b remains a captivating subject of study in understanding extreme planetary environments, yet it presents unique challenges that render it inhospitable to human explorers and conventional spacecraft. Its study, however, provides invaluable insight into the nature of planets at the edges of habitability and the forces that shape distant worlds. Though Glia 436b and Neptune share a classification as Neptune-like planets, the two differ significantly in size and composition. Both are classified as gas giants, but Glia 436b stands apart due to its proximity to its host star, which results in its much higher surface temperatures. In terms of size, Glia 436b is smaller than Neptune. While Neptune has a diameter of about 30,000 miles, Glia 436b's diameter is approximately 22,000 miles. This difference in size gives Glia 436b a smaller volume and mass, though it still retains the defining characteristics of gas giants. The compositions of the two planets also differ greatly. Neptune's atmosphere is predominantly composed of hydrogen, helium, and methane, which gives it its signature blue hue. Glia 436b, though likely composed mainly of hydrogen and helium as well, is distinguished by its higher densities, which suggest the presence of heavier elements and compounds. The extreme pressure within Glia 436b's atmosphere leads to the existence of hot ice or supercritical liquids, phenomena that do not occur on Neptune. While Neptune's atmosphere is relatively cold, with temperatures hovering around 9 or 300 degrees Fahrenheit, Glia 436b's proximity to its host star results in scorching temperatures that can exceed 700 degrees Fahrenheit. These vastly different conditions lead to unique atmospheric phenomena on each planet, influencing cloud formations, wind patterns, and overall weather systems. Glia 436b's atmosphere behaves in ways completely distinct from Neptune's, offering scientists a rare glimpse into how extreme heat and pressure can shape a planet's climate and atmospheric dynamics. Glia 436b and Neptune, both classified as gas giants, offer a stark contrast in their size, composition, and environments. Despite their shared classification, these differences provide a unique lens through which we can explore the incredible diversity of planetary systems. This variance enhances our understanding of the conditions that can exist across the universe, offering valuable insights into the vast range of planetary environments beyond our own solar system. Studying Glia 436b in particular has opened a window into how water behaves under extreme conditions, offering a glimpse into the physical and chemical properties of water when exposed to both intense heat and pressure. As a hot Neptune, Glia 436b experiences temperatures exceeding 700 degrees Fahrenheit, about 371 degrees Celsius, accompanied by atmospheric pressures far greater than those found on Earth. These extreme conditions create environments where water can take on entirely new states that are as fascinating as they are critical for understanding the fundamental nature of this vital substance. One of the most groundbreaking revelations from Glia 436b is the concept of supercritical water. Under conditions of extreme heat and pressure, water transitions into a state that combines properties of both liquid and gas. In this supercritical state, water no longer behaves like a typical liquid. It can dissolve substances and flow through materials similarly to a gas, but retains the dense flowing quality of a liquid. This unique state of water is crucial for scientists aiming to understand its chemical interactions, its solubility, and the reactions that could occur under such otherworldly conditions. The study of supercritical water on Glia 436b doesn't stop there. It extends to the behavior of water ice in high-pressure environments. On this exoplanet, scientists can investigate how water transforms into different types of ice when subjected to extreme temperatures and pressures. This research can reveal crucial details about the crystalline structure of ice, providing us with deeper insights into its formation and stability. Such knowledge can be applied to understand the behavior of ice on other celestial bodies such as Europa or Enceladus, moons of Jupiter and Saturn known for their thick, icy shells. It could also help refine theories on the presence of water ice in massive planetary atmospheres or in deep space environments. But Glia 436b is more than just a lab for studying water. It also plays a key role in our search for extraterrestrial life. By understanding how water behaves in extreme environments, scientists can extrapolate this knowledge to other planets and moons that may host similar conditions. This comparison is essential in evaluating the habitability of distant exoplanets, or even our own solar system's moons, such as Europa or Enceladus, where subsurface oceans could harbor life in ways we are only beginning to understand. The findings from Glia 436b stretch beyond the study of water. By unlocking the secrets of how water behaves under such extreme conditions, scientists are uncovering a host of other valuable insights. These discoveries have the potential to advance fields like planetary science, material science, and chemistry. They may even revolutionize our understanding of physical and chemical processes occurring across diverse celestial environments, from the surface of exoplanets to the interiors of distant stars. To study these extraordinary properties, scientists rely on a combination of observational techniques and cutting-edge simulations. One of the primary methods for studying exoplanets like Glia 436b is transit photometry. This technique monitors the brightness of a star as the planet passes in front of it. As Glia 436b transits, the dimming of the star's light provides indirect evidence of the planet's size and offers clues about its atmospheric composition. The data collected during these transits can also help reveal the conditions on the planet's surface, from temperature gradients to cloud formation. In addition to transit photometry, spectroscopy plays a pivotal role in understanding the composition of Glia 436b's atmosphere. As the starlight filters through the planet's atmosphere during a transit, specific wavelengths of light are absorbed by different molecules present in the atmosphere. By analyzing this spectrum, scientists can identify the chemical makeup of the atmosphere, revealing the presence of exotic elements or compounds that could explain the planet's unique properties, such as supercritical water or other unusual materials. However, observational techniques alone are not enough to fully comprehend the complexities of Glia 436b. Researchers also rely on computer modeling and simulations. These models are based on the known laws of chemistry and physics, simulating how various compounds, particularly water, behave under the extreme conditions found on the planet. These simulations can predict how the planet's surface might appear, how water and other substances would interact in such environments, and even what states of matter might emerge. By refining these models, scientists can make educated predictions about the conditions on Glia 436b and its potential to reveal new, unexpected phenomena. In the end, the study of Glia 436b does more than simply advance our understanding of water and planetary environments. It challenges our imagination and expands the boundaries of what we thought was possible, offering tantalizing clues about the diversity of worlds that populate our universe. By continuing to study exoplanets like Glia 436b, we are not just observing distant planets, we are pushing the limits of our knowledge about the very nature of matter, chemistry, and life itself. In the quest to understand distant worlds, scientists rely on a blend of cutting-edge observational techniques and comparative studies, drawing insights from similar exoplanets and extreme conditions both here on Earth and throughout our solar system. By examining these parallels, researchers can form a more detailed and dynamic understanding of what might await on distant planets like Gliese 436b. While studying a far-off planet such as Gliese 436b comes with its challenges, the synergy between real-time data from telescopes, sophisticated computer modeling, and comparisons with known planetary environments equips scientists with a powerful toolkit. This enables them to unravel the mysteries of this distant world's unique surface and atmosphere. Gliese 436b is a planet that presents one of the most fascinating extremes in planetary science, a world where hot ice is the norm. Such an environment likely features an atmosphere shaped by immense pressures and temperatures that are foreign to us on Earth. The planet's proximity to its host star, where thermal energy is constantly being radiated, plays a pivotal role in molding its atmospheric characteristics. This heat, combined with the planet's specific chemical composition, results in an atmosphere vastly different from anything we experience on our own planet. The atmosphere on Gliese 436b would likely be dominated by hydrogen and helium, much like other gas giants, but it may also contain heavier elements and compounds formed under extreme pressure. At the heart of the planet's atmospheric dynamics lies the presence of supercritical water, a state of matter where water exists in a form that blends liquid and gas properties. In this unique state, water exhibits enhanced solubility, allowing for interactions with a variety of substances. This could lead to the formation of exotic clouds or other atmospheric phenomena not seen in more familiar planetary environments. With such high temperatures, the atmosphere of Gliese 436b could also harbor vast quantities of water vapor. However, unlike Earth's oceans or clouds, this vapor would not condense into liquid or solid water. Instead, the conditions on the planet would foster a highly complex chemical environment, with trace gases such as ammonia, methane, or even carbon-based compounds potentially forming. These substances would interact in ways we can only begin to imagine, potentially creating environments rich with chemical variety. Furthermore, the relentless energy supplied by the nearby star would provoke intense weather patterns. The resulting high winds, rapid temperature shifts, and unpredictable conditions could give rise to powerful storms and other dynamic systems. Temperature variations across the planet, caused by the planet's rotation and the interaction of materials in dual states, might lead to sharp gradients, generating extreme weather systems that are both violent and awe-inspiring. In essence, Gliese 436b represents a planet whose atmosphere combines extreme temperatures, intense pressures, and the kind of complex chemistry that challenges our understanding of planetary systems. The behaviors and interactions of its materials provide a striking contrast to those found on terrestrial planets or even more typical gas giants, such as Neptune. Studying this kind of atmosphere not only expands our knowledge of how materials behave under such extremes, but it may also reveal exotic forms of chemistry that differ dramatically from what we observe in more familiar environments. Currently, Gliese 436b maintains a relatively stable state akin to that of a hot Neptune. Its steady orbit around its host star ensures a consistent influx of thermal energy, which sustains the planet's unique atmospheric conditions, including the existence of hot ice. The balance between gravitational forces and thermal energy received from the star helps keep Gliese 436b in this stable state. However, this equilibrium is not guaranteed forever. Over time, various factors could cause the planet to evolve. One key element influencing Gliese 436b's future is its proximity to its host star. Orbiting so close, the planet is bombarded by intense stellar radiation, which continuously impacts its atmospheric makeup and thermal dynamics. This prolonged exposure could eventually result in atmospheric erosion, especially if the star undergoes changes in its life cycle. If the star becomes more active, it could strip away large portions of the planet's atmosphere, altering the pressures, temperatures, and possibly the chemical composition of the planet's environment. As Gliese 436b continues its orbit around its host star, scientists will be watching closely, using the wealth of data at their disposal to predict what changes might occur in this volatile and captivating world. Through this research, we inch closer to understanding not just this planet, but the broader mechanics of planetary atmospheres in our universe, opening the door to even more extraordinary discoveries. Beneath the immense heat and staggering pressures of Glia 436b, profound changes in the planet's material makeup are slowly unfolding. The interactions between heat and the planet's atmospheric components might trigger chemical reactions, transforming existing compounds, or even creating entirely new ones. Over time, these shifts could alter the stability of its atmosphere, potentially reshaping the very surface of the planet itself. In this harsh environment, every element is at the mercy of the extreme forces at play. But it's not just the intense atmospheric conditions that could lead to dramatic transformations. The orbital stability of Gliese 436b is equally crucial. Any disturbances caused by gravitational interactions with neighboring celestial bodies or fluctuations in the energy output of its host star could have significant repercussions on the planet's orbit. Even subtle variations in its orbital path would trigger shifts in temperature and pressure, further complicating the atmosphere and surface conditions. While Gliese 436b currently maintains a relatively stable hot Neptune state, a multitude of dynamic factors, from stellar activity to atmospheric changes, could alter its long-term stability. Understanding these shifting dynamics is key to unraveling the planet's evolutionary path. It offers a glimpse into the broader processes at work on planets under extreme conditions, expanding our understanding of exoplanets across the universe. Exotic matter in extreme conditions. The extreme conditions on Gliese 436b, marked by high temperatures and intense atmospheric pressures, open the door to the existence of exotic forms of matter. The planet's unique environment may give rise to substances that challenge our conventional understanding of chemical and physical properties. Among these forms is supercritical water, a substance that exists under such high pressures and temperatures that it neither behaves strictly as a liquid nor as a gas. In this state, water takes on extraordinary solubility properties, allowing it to interact with other materials in ways that could lead to complex chemical reactions and the creation of unusual compounds. Moreover, the extreme pressures on Gliese 436b could lead to the formation of ice structures unlike anything we know on Earth. These ice phases, such as Ice 7 or Ice X, form only under extreme conditions far beyond Earth's surface. These dense, unique forms of ice would not only transform the planet's geology, but could also dramatically impact its atmosphere. Another potential exotic material to emerge on this world is metallic hydrogen. Under Gliese 436b's crushing pressures, hydrogen may shift from its gaseous form into a metallic state, exhibiting properties similar to metals, such as electrical conductivity. The presence of metallic hydrogen could influence the planet's magnetic field, contributing to strange atmospheric phenomena and perhaps even triggering violent electrical storms. Furthermore, the planet's volatile mix of gases, ammonia, methane, and other hydrocarbons, could interact in entirely new ways. These interactions might give rise to bizarre chemical compounds, possibly creating lakes of liquid methane or clouds formed from complex organic materials. These materials could be the building blocks for entirely novel forms of life, or they may simply highlight the incredibly diverse chemistry possible under extreme conditions. Each of these exotic states of matter challenges our existing scientific models, prompting us to rethink how materials behave when pushed to their limits. By studying these extraordinary phenomena on Gliese 436b, scientists gain invaluable insights not only into this distant planet, but also into the fundamental principles that govern matter throughout the universe. Thea Prime, the birth of a planetary collision. In the early history of our solar system, a dramatic planetary collision is thought to have led to the formation of Thea Prime, a precursor to Earth. This theory is supported by both astronomical observations and sophisticated computer simulations of planetary formation. These simulations reveal the tumultuous process that occurred as protoplanets began to coalesce, a time when collisions were common, and celestial bodies vied for space in an unstable and dynamic environment. The evidence suggests that the Earth we know today owes its existence to this chaotic phase of planetary evolution. Through a series of cataclysmic impacts, the solar system began to take shape, setting the stage for the emergence of Earth, its moons, and the life forms that would later populate its surface. The surface of the moon offers us a vivid, real-world window into a time long past, one marked by violent impacts and cosmic upheaval. Its heavily cratered landscape, pockmarked with evidence of cataclysmic collisions, speaks to an era when the solar system was anything but peaceful. These scars, left behind by both small meteoroids and large protoplanets, tell a tale of a time when Earth, the Moon, and other bodies in the solar system were bombarded by relentless cosmic forces. Through careful analysis of lunar samples, scientists have been able to determine the ages of various craters, drawing a direct connection between these ancient impacts and the larger models of solar system evolution. This evidence not only supports the idea that such intense collisions were not just possible but highly likely, but it also helps illuminate a fascinating chapter of our cosmic history. The study of exoplanets, planets orbiting distant stars, adds even more weight to this hypothesis. Many of these planetary systems exhibit signs of dynamic chaos, unusual orbital patterns, strange debris disks, and the unmistakable remnants of past collisions. Observations from advanced telescopes have revealed that some planetary systems are in a state of disarray, where planetary orbits are disrupted by the violent gravitational interactions of colliding bodies. These disruptions suggest that massive impacts played a key role in shaping the configurations of these distant worlds. One of the most compelling pieces of evidence for such planetary collisions comes from isotopic analysis of both Earth and Moon samples. The similarities between these two bodies suggest they share a common origin, a theory supported by the impact of a Mars-sized object in the early days of Earth's formation, often referred to as Theia Prime. This colossal collision would have resulted in debris that eventually coalesced into the Moon, a cosmic sibling forged from the same violent past. The evidence aligns perfectly with other observations of widespread energetic collisions in the early solar system, underscoring the notion that planetary collisions were not only possible, but integral to the evolution of the planets we know today. In the immediate aftermath of Theia Prime's colossal impact, the surface of the Earth would have been an arena of chaos and destruction. Picture a world where superheated rock and molten material swirl through an atmosphere thick with dust and vapor. The shock of the collision would have shattered the surface, causing massive upheaval and creating vast fissures and craters that mark the landscape for millions of years. At first, these craters would have been unimaginably deep, cutting into the planet's surface like the marks of a cosmic artist, leaving behind scars that spoke of a brutal birth. Above, the atmosphere would have been dense and choking, a tumult of volcanic gases, steam, and particles obscuring the sky. This temporary atmosphere would have been incredibly hot, with temperatures soaring far beyond anything we would consider survivable. As time passed, this atmosphere would slowly begin to thin, but not without leaving behind a world with a constantly shifting, unstable surface. The cooling of molten rock would eventually form a new crust, yet it would be anything but uniform. The remnants of the initial collision, along with the ongoing volcanic activity and impacts from leftover debris in orbit, would create a surface full of irregularities. Pockets of lava would still bubble beneath the surface, occasionally breaking free in fiery eruptions. Through this tumultuous period, the interplay of gravitational forces would continue to shape the planet, with large bodies of debris, fragments of Theia and Earth, either crashing back down or merging into new formations. This violent chapter in the planet's history would give rise to a harsh, rugged terrain, setting the stage for a more stable future. At this point, any atmosphere the planet might have had would have been in turmoil, constantly altered by the ongoing impacts. The immense energy released during these collisions could have easily stripped away any existing atmosphere or radically altered its composition. Following a collision, the planet would have been surrounded by a temporary atmosphere composed of superheated gases and vapor. This chaotic, volatile environment would be predominantly made up of steam, carbon dioxide, and other volatile compounds released by the planet's crust. With each new collision, this atmosphere would continue to evolve, shifting rapidly with every impact. If the planet was fortunate enough to retain some form of atmospheric integrity, the combination of heat and constant debris would likely have resulted in a high-pressure environment, one that could trap gases and create a thick, toxic atmosphere. In such conditions, life as we know it would have been impossible. The atmosphere would also have been marked by intense weather phenomena, such as thunderstorms fueled by the ongoing volcanic eruptions and violent winds sweeping through the thick clouds of gas and ash. Sunlight would have struggled to penetrate this murky shroud, leaving the surface in near constant darkness. Over time, the cycle of collisions would have continued, altering the planet's atmosphere and surface. How often and how violently these impacts occurred would determine whether the planet could eventually stabilize. If the planet managed to find some equilibrium, it might have begun to develop a more temperate atmosphere, allowing surface conditions to normalize and laying the groundwork for future habitability. This chaotic birth, marked by the force of catastrophic collisions, would eventually lead to the formation of a more stable environment, a planet destined to evolve, stabilize, and perhaps one day harbor life. However, while active collisions persist, the atmosphere would remain a fierce and unpredictable environment, mirroring the violence and chaos of its surroundings. As two astronomical bodies draw closer, preparing to merge, the behavior of gravity evolves into a complex and dynamic force. Initially, gravity acts as the primary driver, pulling the two bodies together. The gravitational pull between a larger entity, such as a planet, and a smaller one, like an asteroid or a minor planet, grows exponentially stronger as they approach each other. This intensifying interaction creates tidal forces that distort both bodies' surfaces, forming bulges and extensions that stretch their shapes beyond their normal proportions. As the bodies collide, these gravitational forces become far more dramatic, resulting in substantial variations in gravity across their surfaces. Close to the point of impact, gravity would be extraordinarily intense due to the immense mass concentrated there. In contrast, regions farther away would experience a diminished pull. This sharp contrast in gravitational forces could lead to fascinating phenomena, such as debris being flung outward into space, or even creating new orbital configurations for nearby moons or celestial objects caught within the gravitational reach. A particularly striking aspect of this collision occurs when one body begins to break apart due to the overpowering gravitational forces. If the two bodies involved are significantly unequal in size, the smaller one may disintegrate upon impact. The resulting fragments would be subject to the gravitational pull of the larger mass, pulling them into temporary orbits around it. These fragments might either be drawn toward the surface of the larger body or flung outward into space, creating a turbulent environment of shifting masses. As the merging continues, gravity will play a central role in redistributing material from both bodies. The immense heat and pressure generated by the collision could melt and mix the material, with gravity pulling molten and solid substances toward the center of the newly forming mass. Over time, as the two bodies merge and the environment stabilizes, gravity will work relentlessly to form a new singular body, its properties shaped by the remnants of both original bodies. This chaotic interplay of gravitational forces highlights gravity's essential role in shaping celestial formations throughout the universe. From the surface of Theia Prime, the sky, during this collision process, would present a breathtaking yet terrifying spectacle. Before the impact, as two massive bodies draw near, the sky would be dominated by the ominous silhouette of the approaching object. Depending on its size, it might fill a significant portion of the sky, casting a shadow across the landscape, invoking an eerie twilight effect even during the day. The atmosphere would be thick with turbulence, swirling clouds disrupted by shock waves and atmospheric disturbances. As the collision draws closer, the sky would shift into a kaleidoscope of colors, caused by the extreme heat and gases released from both bodies. Bright flashes of light would punctuate the turbulent clouds as fiery debris is ejected, illuminating the landscape in brief bursts of brilliance. Vivid storms and lightning would ignite, creating a cacophony of colors, deep reds, oranges, and yellows, set against the darkened backdrop of ash and vapor-filled clouds. With every moment leading up to the impact, the sky would grow more chaotic. Thick plumes of smoke and vapor would rise from the surface, obscuring the horizon and shrouding parts of the sky in a blanket of haze. The atmospheric pressure created by these events would cause the clouds to form in layers, with dense lower-level formations hugging the surface, while higher layers, potentially charged with electricity, would rumble ominously. The sound of the impending collision might amplify this scenario, with echoes of distant impacts reverberating across the landscape, heightening the sense of approaching destruction. In the wake of this colossal event, the sky would continue to shift and transform, providing a constant reminder of the power and unpredictability of cosmic collisions as gravity continues to sculpt the universe around it. Just before the colossal impact, a brilliant flash of light might illuminate the sky as the smaller solar celestial body crashes into Theia Prime. The collision would release energy equivalent to countless nuclear explosions, an event so powerful that it would not only light up the sky, but also mark the beginning of a dramatic transformation for the planet. This moment would forever alter its surface and atmosphere, setting the stage for a new chapter in its formation. The sky, ablaze with energy, would be a stunning yet devastating display of cosmic power, a vivid reminder of the raw forces shaping the universe. The collision of two planetary bodies, such as Theia Prime and another massive object, unfolds over a period of time, often stretching from several hours to days. The exact duration depends on variables like the sizes and speeds of the colliding objects, as well as their gravitational fields. This cataclysmic event can be divided into distinct stages, each characterized by specific physical processes and transformations. The first stage, known as the approach phase, involves the two bodies slowly drawing closer, their gravitational fields beginning to distort their shapes. This phase can last anywhere from a few hours to several weeks, depending on the object's velocities. As they approach each other, tidal forces intensify, creating massive bulges in their surfaces, warning signs of the impending impact. The sky would grow turbulent with increasing atmospheric disturbances caused by the gravitational forces at work. The next stage is the collision itself, where the two bodies collide with immense force. This moment is marked by the release of unimaginable energy, triggering shock waves that ripple through both masses. Craters would form, and vast amounts of debris would be ejected into the atmosphere, creating towering plumes of dust and rock. Although this stage happens relatively quickly, its consequences are far-reaching, as it symbolizes the merger of two separate entities into one unified mass. Once the collision occurs, the merger stage begins. The debris, now scattered throughout the atmosphere, would begin to coalesce under the influence of gravity. As the materials mix and melt, the temperature rises dramatically. This stage, which can last anywhere from days to weeks, marks the gradual transition from chaos to stability. Intense volcanic activity would dominate the landscape, heating the newly forming planetary body and facilitating the creation of a crust over time. Through this period of violent transformation, the surface would eventually stabilize, allowing for the formation of a singular planetary body. The process would also pave the way for the cooling of the crust and the eventual development of an atmosphere, a crucial step in the planet's evolution. This journey through planetary formation offers a glimpse into the dynamic nature of cosmic change, illustrating the profound reshaping of a celestial body. As the merger of Theia Prime progressed, the geological activity would be nothing short of extreme. The initial impact would unleash a tremendous surge of energy, melting vast portions of rock and generating shock waves that travel deep within the planet's crust. This would trigger powerful earthquakes, capable of reshaping the surface in moments. These seismic activities would give birth to new geological features. Huge fissures, massive craters, and towering mountain ranges formed as the crust responded to the overwhelming stresses of the impact. Following the collision, volcanic activity would dominate the landscape. The heat and pressure generated from the impact would melt both planetary bodies, causing molten material to rise to the surface in the form of lava flows, eruptions, and pyroclastic activity. These eruptions would be extraordinarily violent, hurling ash and gas into the atmosphere and contributing to a thick global cloud cover. This, in turn, would radically alter Theia Prime's climate and surface conditions. The landscape would be in constant flux, reshaped by the intense forces of volcanic activity. Even after the initial impact and volcanic eruptions, the geological processes would continue, driven by the residual heat from the collision and the ongoing gravitational interactions. Mantle convection would be at its peak, fueling further tectonic movements and volcanic eruptions. Gravity would continue to shape the surface, leading to the formation of valleys, plateaus, and in some cases, crater lakes, depressions formed by the impacts that eventually fill with molten rock. As time passed and Thea Prime began to cool, geological activity would persist, though at a reduced scale. Over time, the planet's surface would settle into a more stable configuration, laying the foundation for the eventual emergence of an atmosphere and the possibility of life. The formative process, driven by cosmic collisions and internal heat, would serve as a testament to the relentless forces at play in the creation of planetary bodies, forever altering the course of Thea Prime's evolution. However, the legacy of a violent past would endure, leaving an indelible mark in the form of rugged terrain, a patchwork of volcanic landforms, and a potentially distinct internal structure that reflects the tumultuous processes of planetary merger. This intense geologic activity serves as a vivid reminder of the dynamic and ever-changing nature of planetary formation, showcasing how cataclysmic events can deeply influence a planet's geological makeup and the landscape that emerges from it. The collision of two massive planetary bodies like Thea Prime and another celestial mass would reverberate across the entire solar system. Such a cataclysmic event wouldn't just affect the immediate vicinity. It would send shockwaves across the heavens, leaving its mark on moons, planets, and even smaller bodies scattered throughout the system. The violent nature of this collision would unleash powerful gravitational disturbances, sparking a chain reaction that could affect celestial bodies light years away from the original impact. Moons orbiting Thea Prime would be particularly vulnerable. As gravitational forces fluctuated during the impact, depending on their proximity to the collision, these moons might experience dramatic shifts. Intense tidal forces could warp their orbits, and in extreme cases, they could be torn apart. The collision would likely generate massive amounts of debris, casting fragments of rock, ice, and dust into space. This debris could form a ring system around the planet or contribute to existing asteroid fields. Some of this material might even be drawn into the orbits of nearby moons, leading to further chaos. Collisions, tidal forces, and destructive interactions would be the result. For planets near Thea Prime, the consequences would be similarly catastrophic. The aftermath of such a monumental impact would likely alter their orbits, as the sudden release of energy and mass would send out gravitational waves that ripple through the fabric of the solar system. Nearby planets might find their paths shifted, or they could experience a heightened bombardment from the debris cast into space. Smaller bodies already situated in the asteroid belt would also feel the effects, as the collision's energy could push them off their usual trajectories, leading to even more collisions and disruptions. But the effects of the impact wouldn't be confined to just physical destruction. The collision could trigger atmospheric and climatic changes across the solar system. Ejected material could penetrate the atmospheres of moons and planets, altering their compositions. If any of these bodies had conditions suitable for life, the sudden influx of gases, dust, and particles could wreak havoc, changing the climate and possibly even wiping out ecosystems that had previously thrived. In essence, the collision would set off a domino effect, sending ripples throughout the entire solar system. It would highlight the intricate interconnectedness of celestial bodies and the delicate balance maintained by gravitational forces. Such a catastrophic event demonstrates how the fate of one body can have far-reaching consequences on others, underlining the chaotic and dynamic nature of planetary systems. Studying theoretical planets like Thea Prime offers invaluable insights into the formation of Earth and its moon. Much of our understanding of these origins is rooted in the theory that large-scale impacts played a pivotal role in shaping the planetary system. The idea that Thea, a Mars-sized body, collided with the early Earth is central to the giant impact hypothesis, which posits that such colossal collisions were not just possible, but likely in the volatile early solar system. One of the key revelations from models of planets like Thea Prime lies in the dynamics of planetary accretion, the process through which debris from a violent collision coalesces to form a moon. This is believed to have happened with Earth's moon. Through various simulations and models, scientists can better understand the specific conditions and characteristics required for a successful merger that results in a stable orbit and a moon-like body. By studying these planetary dynamics, scientists gain a clearer picture of the complex interactions that drive the formation of celestial relationships, helping us to uncover the precise trajectories, sizes, and compositions needed to forge such systems. The information extracted from these models doesn't just expand our understanding of the early solar system, it also offers vital clues into the forces that shaped our planet and the moon that orbits it. Moreover, theoretical studies provide an invaluable window into the possibilities surrounding the composition and chemistry of both Earth and Theia. Through isotopic analyses of lunar samples, researchers have uncovered striking similarities with terrestrial rocks, strongly suggesting that the Moon and Earth share a common origin. By studying the potential makeup of Theia, scientists can reconstruct the specific conditions that would have been necessary for these matches to emerge. The examination of hypothetical planetary bodies like Theia is crucial, as it helps refine our understanding of the materials and processes that govern planetary formation, shedding light on the roles of metals, rock, and volatile compounds in shaping worlds. Furthermore, these investigations underscore the significance of examining impact dynamics beyond just Earth and its moon. Expanding the scope of study to include other celestial bodies and their moons offers researchers a broader understanding of the formation histories across the solar system. This, in turn, enriches our grasp of planetary evolution and helps explain the behaviors of systems similar to our own. Ultimately, this knowledge delivers a clearer, more comprehensive picture of our place within the cosmos. The study of theoretical planets exemplifies how investigating the past not only deepens our comprehension of present conditions, but also opens pathways to predicting future possibilities. Whether in our solar system or beyond, these studies offer valuable insights into the complex processes that govern planetary formation and evolution. Now, imagine the unimaginable. If life had existed on either of the colliding planets, the effects of such a monumental event would be catastrophic, yet not entirely annihilating. The immediate aftermath of such a collision would likely result in extreme heat, shock waves, and widespread environmental devastation, conditions inhospitable to most known forms of life. The intense energy unleashed could obliterate entire ecosystems, vaporizing bodies of water and transforming biospheres into landscapes dominated by molten rock and ash. However, the potential for life to survive such a cataclysm depends largely on the resilience of the organisms and the nature of their environments. Extremophiles, for instance, are microorganisms capable of thriving in extreme conditions such as high heat, pressure, and radiation. If such resilient forms of life existed on one of the colliding bodies, they might endure the initial wave of heat, entering dormancy to survive the aftermath. These organisms could find refuge in deep subsurface environments or hydrothermal vents, where the impact's destructive forces would be less severe. In these protected niches, life could persist, sheltered from the immediate dangers of the surface. Moreover, some organisms might find sanctuary within the ejecta, debris blasted from the planetary surface during the collision. This material could provide insulation from the extreme conditions, offering a rare chance for survival until the environment began to stabilize. When conditions finally cooled and settled, these organisms might re-emerge, potentially adapting to the new realities of their transformed world. As the post-collision landscape began to stabilize, the opportunities for colonization would grow. Volcanic activity and the formation of new landmasses would likely create niches rich in minerals and other resources, offering a new beginning for life. Over time, as ecosystems slowly re-establish themselves, the survivors of the catastrophe could evolve and diversify to adapt to the newly shaped environment. While the collision would irrevocably alter the planetary bodies involved, life's resilience and capacity for adaptation would be the key to its persistence. By studying these scenarios, we gain deeper insights into the tenacity of life, illustrating how it could survive even in the harshest of conditions. This research broadens our understanding of how life might emerge and endure in extreme environments, not only within our solar system, but across the vast expanse of the cosmos. In the realm of planetary science, supercritical water presents a fascinating state of matter, occurring when water is subjected to high temperatures and pressures, specifically above its critical point of around 371 degrees Celsius and 226 atmospheres of pressure. In this state, water behaves very differently from its more familiar liquid form. Under standard conditions, water exists in three distinct states: solid, liquid, and gas. These states are clearly defined, with distinct boundaries separating the liquid and vapor phases. However, once water reaches its supercritical state, it transcends these boundaries and takes on properties of both a liquid and a gas. In this supercritical state, water becomes a unique solvent, capable of dissolving non-polar compounds like a gas, while still retaining some of the fluidity of a liquid. This ability makes supercritical water a powerful tool for various chemical processes. Its density is lower than that of liquid water, but higher than that of water vapor, which enables it to penetrate materials more easily. These extraordinary properties of supercritical water make it an invaluable substance in a wide range of scientific fields, including chemistry and planetary science, where it plays a key role in understanding material interactions under extreme conditions. Supercritical water, a state of water that exists under conditions of both high temperature and pressure, exhibits remarkable properties that distinguish it dramatically from regular liquid or gas. Its higher diffusivity makes it far more effective at dissolving gases and organic materials, enabling it to facilitate chemical reactions at rates much faster than those observed in typical environments. This unique characteristic is harnessed in a variety of technologies, most notably in organic waste treatment and green chemistry. In industrial applications, the differences between supercritical water and normal water have profound implications. One such application is supercritical water oxidation, SCWO, a process that is particularly useful for the treatment of organic waste. Through this method, harmful substances are effectively processed, converting them into less hazardous materials. This process demonstrates how an in-depth understanding of supercritical water's properties has spurred innovations in waste management and resource recovery, showcasing its versatility and importance in environmental science and industrial processes. Now imagine a planetary ocean entirely composed of supercritical water. Known as Oceanus Extremis, this hypothetical concept is often used in discussions about extreme planetary environments. It suggests a scenario in which water maintained above its critical point, approximately 371 degrees Celsius and 226 atmospheres of pressure, exists as a supercritical fluid throughout the depths of an entire ocean. To sustain such an environment, a planet or moon would require a substantial gravitational field capable of holding a dense atmosphere that could maintain these elevated pressures. Such high pressure prevents the formation of water vapor, ensuring that the entire ocean remains in a supercritical state. In this extreme scenario, a strong geothermal gradient would likely play a vital role, providing the heat necessary to maintain the required temperatures. This heat might come from active volcanism or tectonic activity, where energy from the planet's interior is continuously released. An atmosphere rich in greenhouse gases, such as carbon dioxide and methane, would trap heat effectively, keeping the planet's surface hot enough to sustain supercritical water. The thick atmosphere would minimize heat loss to space, stabilizing the environment and allowing conditions favorable for a global ocean of supercritical water. Even the composition of this atmosphere could have profound effects on the dynamics of the supercritical ocean. The presence of various solutes dissolved in the water might alter the temperature and pressure at which supercritical water can exist. This would allow for localized variations within the ocean while still maintaining overall supercritical conditions. By understanding these factors, scientists gain critical insights into the potential development of extreme environments on distant exoplanets or moons. These insights could offer clues about how life might evolve in such alien conditions, or even reveal unique geochemical processes that could emerge in such extreme oceans. The idea of Oceanus Extremis challenges our conventional understanding of habitability and highlights the astonishing diversity of planetary environments that could exist throughout the universe. The properties of supercritical water would also have profound implications for a planet's geology. Its enhanced solvent capabilities and ability to dissolve a wide range of substances would accelerate geological and chemical processes that could reshape the planet's surface. Supercritical water could act as a potent agent of erosion and mineral transport. Its ability to infiltrate rock formations would enable it to dissolve minerals more efficiently than regular liquid water, leading to the alteration of geological features and the creation of new formations. This process could give rise to unique hydrothermal systems where supercritical water interacts with hot rocks to form mineral deposits. These deposits could eventually lead to the creation of hydrothermal vents, hotspots of geological activity where life might emerge. Just as Earth's hydrothermal vent ecosystems are home to unique and resilient organisms, a similar environment on a distant planet could foster the development of life forms adapted to these extreme conditions. Supercritical water, in essence, could offer a unique biochemical environment where life, if it existed, could thrive by exploiting the solvent properties of water at extreme temperatures and pressures. Organisms in such an environment might evolve to utilize the enhanced solvent capabilities of supercritical water, gaining access to energy and nutrients locked within geological materials that would otherwise remain untapped. The extreme conditions could foster the evolution of extremophiles, organisms adapted to survive in high-pressure, high-temperature environments, much like those found in Earth's deepest oceans. Ultimately, the concept of supercritical water and its potential applications both on Earth and in extreme extraterrestrial environments opens up fascinating possibilities for both scientific inquiry and the search for life beyond our planet. By harnessing the unique properties of supercritical water, we may one day unlock new methods for waste treatment, resource extraction, and even discover entirely new forms of life in places we never thought possible. The presence of supercritical water, water that exists at extreme temperatures and pressures, holds the potential to drastically alter a planet's climate and atmospheric dynamics. If supercritical water were to cycle periodically through various phases, transitioning between vapor and liquid states, it could lead to dramatic shifts in surface temperatures, weather patterns, and nutrient distribution. If this kind of cyclical change would foster a dynamic environment, capable of supporting diverse ecological niches. Such environments could defy conventional views on habitability, offering insights into life's potential in extreme conditions. By exploring the role of supercritical water, scientists can not only expand our understanding of hypothetical planets like Oceanus Extremis, but also enhance the search for life on icy moons and other distant celestial bodies within our solar system and beyond. But imagine approaching a hypothetical world such as Oceanus Extremis. The supercritical ocean presents challenges far beyond the limits of what we know from our own oceans. The conditions here are far harsher, with temperatures that could exceed 371 degrees Celsius and pressures that could surpass 226 atmospheres. For humans, the encounter would be immediately catastrophic. The extreme heat would cause severe burns, and conventional protective gear would fail to withstand such intense conditions. A human body exposed to such temperatures would suffer irreversible damage. The intense pressures would be no less deadly. At over 226 atmospheres, the immense weight of the surrounding water would crush any human body, overwhelming even the most robust materials designed for survival. The structural integrity of spacesuits, protective fabrics, and life support systems would be breached almost instantly. Spacecraft, too, would face similar perils. Although designed to endure considerable extremes of temperature and pressure, the supercritical environment would quickly exceed their design limitations. The materials that make up spacecraft are not built to withstand continuous exposure to such heat and pressure, and they would degrade rapidly. Critical components such as navigation and monitoring systems would become useless within moments of entering this hostile environment. Buoyancy presents another significant obstacle. As water transitions into the supercritical state, its density changes unpredictably, causing erratic buoyancy forces. A spacecraft might rapidly sink or face sudden, intense pressure changes that could result in catastrophic implosion. Without the necessary advanced technology to withstand supercritical conditions, both human crews and conventional spacecraft would face insurmountable challenges. This supercritical ocean serves as a reminder of the harsh realities of exploring alien worlds. It underscores the immense complexity and difficulty of understanding environments radically different from those on Earth. Exploring such extreme environments would require groundbreaking advancements in technology, enabling us to push the boundaries of what is possible in space exploration. But what exactly is supercritical water? It's a unique state of water that occurs when both temperature and pressure exceed specific thresholds, above 373 degrees Celsius and 22 megapascals. In this state, water loses its familiar liquid properties, behaving more like a gas, yet retaining the density of a liquid. This transformation has profound implications, particularly in geological and environmental contexts. One of the most significant impacts of supercritical water is its role in nutrient recycling, particularly in geological settings such as subduction zones. In these zones, tectonic plates interact, and supercritical water can facilitate the transport of essential minerals and elements that are vital to sustaining life. Under extreme conditions, water can dissolve minerals more efficiently than in its typical liquid state. This process contributes to the formation of geothermal features and can influence volcanic activity, releasing gases into the atmosphere and impacting local and global climate patterns. In essence, supercritical water holds the potential to shape not only the geological landscape of other worlds, but also the very environments in which life might arise. It challenges us to rethink what constitutes a habitable zone and pushes the limits of our understanding of what is possible in the universe. In the intricate dance of nature's processes, supercritical water plays an unseen yet pivotal role. Under extreme conditions, this extraordinary phase of water is involved in the breakdown of organic matter and the cycling of carbon. In the natural world, water's behavior at high pressures and temperatures affects the rates of oxidation and reduction reactions, driving the release and absorption of gases like carbon dioxide and methane. These gases, often invisible to the human eye, hold immense power in shaping our planet's climate. They act as the gatekeepers of Earth's temperature, regulating it through a delicate balance that influences the concentration of greenhouse gases, ultimately contributing to climate change. But the story doesn't end there. The reach of supercritical water extends beyond the Earth's natural processes. Scientists are now turning to this unique substance as a potential game changer for energy systems. Through processes such as supercritical water gasification, biomass can be transformed into usable energy, offering a promising route toward renewable energy solutions. As we explore this possibility, we not only deepen our understanding of water's extraordinary properties, but we also highlight its potential to shape a sustainable future on a planet whose very nature may be altered by the transition of water into supercritical states. Imagine a planet. Let's call it Oceanus Extremis, where the oceans themselves exist in a supercritical state. The weather patterns on such a world would be utterly unlike anything we experience here on Earth. Supercritical water, a mysterious phase that shares properties of both liquid and gas, would completely transform atmospheric dynamics, heat transfer, and moisture behavior. The implications for climate would be staggering. Temperature regulation, for instance, would see a dramatic shift. Supercritical water has the ability to hold far more heat than ordinary liquid water, leading to a far more even distribution of temperatures across the planet. This could reduce the extreme temperature gradients that typically drive weather systems, resulting in a more stable atmosphere. Large-scale storms might become a rare occurrence, replaced by localized but intense weather events that arise due to rapid shifts in pressure or heat. Yet evaporation and condensation would behave in ways unfamiliar to us. In this state, water wouldn't simply transition from liquid to vapor as we know it. Instead, it would maintain a constant, supercritical state while still exhibiting gas-like behavior. This would likely give rise to strange, unexplained cloud formations and unpredictable precipitation patterns, perhaps dense fog or mist rather than the typical rainfall we're accustomed to. Such changes could foster unique ecosystems and fundamentally alter the biological processes taking place both in the atmosphere and on the surface of the planet. Moreover, the interaction between supercritical water and other elements of the atmosphere could spawn entirely new kinds of storms. These hypothetical storms would have the ability to harness energy directly from the supercritical ocean, resulting in weather systems that defy anything seen on Earth. Expect violent atmospheric disturbances, fierce winds, bizarre cloud formations, and perhaps even continuous lightning. The oddities of supercritical water would reshape the climate and landscape of Oceanus Extremis, creating an environment that challenges all conventional understanding of weather and life. When we think about a world like Oceanus Extremis, we must confront the unique challenges it presents to our understanding of habitability. In such an extreme environment with high temperatures, pressures, and chemical compositions, life as we know it might not survive. The conditions are vastly different from those on Earth, making it difficult to predict what forms of life might emerge, or even if life could exist at all. While extremophiles on Earth showcase the resilience of life, their adaptations might still be inadequate in the face of the extreme conditions found in Oceanus Extremis. So what might life look like in such an alien environment? How would it differ from anything we've encountered on our planet? These are the questions that challenge our understanding of biology and push the boundaries of what we consider possible in the search for life beyond Earth. The chemical composition of Oceanus Extremis will play a crucial role in its ability to support life. If the ocean is filled with toxic substances or is devoid of essential elements like oxygen, the chances for metabolically active organisms to thrive are significantly reduced. This raises an intriguing possibility: life forms that depend on entirely different biochemical systems. Instead of relying on the solvents or energy sources we consider essential, these organisms might use alternative solutions. The presence of extremophilic life on Earth, such as certain archaea and bacteria that flourish in hydrothermal vents, offers a tantalizing glimpse into how life could adapt to the most extreme and alien environments. Exploring Oceanus Extremis forces us to rethink our definitions of habitability. For decades, liquid water was considered the primary requirement for life. However, extreme environments challenge that assumption and suggest that other conditions may also foster life. As a result, the search for extraterrestrial life must now expand and to include environments that defy Earth's conventional understanding of what is habitable. By studying Oceanus Extremis and similar extreme environments, we may come to realize that life is not only possible under such harsh conditions, but that it can be uniquely resilient, adapting to survive in the most hostile corners of the universe. To study a planet with a supercritical water ocean requires advanced methods tailored to its unique characteristics. Remote sensing technology, for example, will be a key tool. Spacecraft outfitted with sophisticated instruments can analyze the light reflected from the planet's surface and atmosphere. By measuring various wavelengths, scientists can detect the chemical signatures of compounds, assess temperature variations, and infer the ocean's state. This data will offer vital information about the planet's dynamic processes, allowing us to understand the behavior of the supercritical water ocean. In addition to remote sensing, lander or probe missions will be indispensable for gathering on-the-ground data. These missions will need to be designed to endure the extreme temperatures and pressures found in the supercritical water ocean. By using specialized sensors, these probes could collect samples and directly analyze the ocean's composition and physical characteristics. The data gathered would not only expand our knowledge of the planet's geology and hydrology, but also shed light on the potential for life to thrive there. A promising addition to these exploration efforts would be the deployment of autonomous underwater vehicles. These robotic crafts would be capable of venturing into the depths of the supercritical ocean, gathering real-time data while performing experiments. Given the extreme conditions of the ocean, these robots would need to be engineered with precision to withstand the high pressures and temperatures, ensuring they could operate without being compromised. This approach could reveal insights into the ocean's circulation patterns, its interactions with the planet's atmosphere, and the overall behavior of this alien environment. Lastly, Earth-based laboratory simulations of supercritical water environments will prove to be invaluable. By recreating the extreme conditions of a supercritical water ocean in a controlled environment, scientists can simulate potential chemical reactions, biological processes, and energy cycles. The insights gained from these experiments will directly enhance our interpretation of data from space missions, providing a clearer picture of what life might look like in such an environment and how it could survive there. Supercritical water's properties could also profoundly impact a planet's geological development. When present in a planet's interior or surface environment, supercritical water alters the behavior of minerals and rocks, playing a pivotal role in geological processes. Unlike normal water, supercritical water can dissolve and transport minerals far more efficiently, accelerating chemical reactions. This ability can lead to the formation of geological features such as hydrothermal vents and mineral deposits, and it can influence tectonic activity by facilitating the movement of tectonic plates. In essence, supercritical water may be a driving force behind the evolution of the planet itself. As we probe the depths of Oceanus Extremis and similar extreme domains, we may begin to see that the boundaries of habitability are far more fluid than once thought. Life, in all its diverse forms, could flourish in ways we have yet to imagine, adapted to thrive where we once believed it impossible. The exploration of these environments not only challenges our understanding of life, but expands our vision of what the universe holds. Supercritical water plays a crucial role in the thermodynamics of a planet, significantly influencing its geological and atmospheric processes. As an exceptional heat conductor, it enhances the transfer of heat from a planet's core to its surface, increasing the overall temperature. This added heat has far-reaching implications, particularly in shaping a planet's geological stability and volcanic activity. Supercritical water's heat retention capacity can trigger more frequent volcanic eruptions, fundamentally altering the landscape. These eruptions release gases like carbon dioxide and sulfur dioxide, which not only reshape the atmosphere, but also profoundly affect the planet's climate. In turn, this transformation could catalyze chemical reactions essential for various biochemical processes, creating conditions that could support the evolution of life. The presence of supercritical water could be a key factor in determining a planet's ability to support or evolve life forms. Its unique properties, such as facilitating chemical reactions and transporting essential nutrients, may promote novel biochemical pathways, allowing life forms to thrive in ways we can't even imagine. Organisms could exploit supercritical water to harness energy and resources far more efficiently than terrestrial life forms. This opens up possibilities for biospheres that are radically different from anything we know, where life would adapt to extreme environments. Moreover, the interaction between supercritical water and other planetary materials could influence a planet's long-term geological and climatic evolution. The constant processes of dissolution, transport, and precipitation might create a feedback loop where geological shifts and atmospheric changes are tightly interconnected. This feedback loop would help us understand not only the current state of the planet, but also the history of its formation and the potential future pathways for its evolution. Investigating extreme environments like Oceanus Extremis could unlock transformative advancements in both technology and space exploration. One of the most promising areas is the development of advanced materials and robotics capable of enduring the high temperatures and pressures of extreme conditions. Supercritical water's unique properties necessitate the creation of resilient technologies, which could eventually be used to improve the design and longevity of exploration instruments. Insights from these studies could also lead to the development of more durable tools for future space missions, enhancing their efficiency and lifespan. In addition, the exploration of supercritical water could revolutionize resource extraction methods on other celestial bodies. Supercritical water has remarkable solvation capabilities, allowing it to dissolve a wide range of elements and compounds. As we learn to interact with and harness this powerful substance, it could enable innovative extraction techniques for minerals and energy resources on asteroids, moons, or other planetary bodies rich in resources. This ability to tap into extraterrestrial materials could be pivotal for sustaining long-term space missions or even building permanent habitats in outer space. Another promising avenue for research lies in astrobiology. By studying the conditions in Oceanus Extremis, we could gain a deeper understanding of life's potential in the most extreme environments. Learning how organisms adapt to high pressure and high temperature conditions would be crucial for identifying life on other planets, particularly those with subsurface oceans like Europa or Enceladus. By pinpointing the biochemical pathways and survival mechanisms that allow life to endure in such environments, we can refine our strategies for detecting biosignatures on distant worlds. In sum, the study of supercritical water is not just a fascinating scientific pursuit. It is a key to unlocking many of the mysteries of planetary formation, evolution, and the potential for life beyond Earth. It holds promise not only for advancing our understanding of celestial bodies, but also for shaping the future of space exploration and technology. The exploration of Oceanus Extremis holds profound implications for the future of human space exploration. Insights gained from this unique environment could directly inform the development of closed life support systems essential for missions to distant worlds. These systems will need to recycle waste and manage resources efficiently, particularly in isolated environments like space. By studying the dynamics of supercritical water, we can uncover innovative solutions to managing water and nutrient cycles. This knowledge will ensure that future habitats, no matter how hostile the conditions, can sustain human life. The research into Oceanus Extremis could fundamentally enhance our technological capabilities, resource management strategies, and even our understanding of life itself, critical components for the long-term success of space exploration. One area where this knowledge could be transformative is in resource management. As we venture further into space, the necessity for self-sustaining habitats will become paramount. Oceanus Extremis could provide the key to mastering these technologies. The extreme conditions of its environment could serve as a testing ground for systems that allow for efficient recycling of water, nutrients, and even air in confined spaces, much like what we will need for sustainable off-world colonies. The lessons learned here could be applied not only to human settlements in space, but also to understanding life's resilience in the most challenging circumstances on Earth and beyond. Now, turning our gaze outward into the cosmos, let us examine magnetars, some of the most extraordinary celestial objects in the universe. These neutron stars possess magnetic fields that are far stronger than those of typical neutron stars, reaching levels that can surpass 1,000 trillion times the strength of Earth's magnetic field. Such immense magnetic forces are the result of the collapse of a massive star during a supernova explosion, which leaves behind a neutron star, a compact, incredibly dense remnant made mostly of neutrons. While the magnetic fields of ordinary neutron stars can be up to 1 billion times stronger than Earth's, the magnetic fields of magnetars can reach truly staggering intensities. These extreme magnetic forces are so powerful they drive phenomena such as bursts of gamma rays and X-rays. The magnetic field of a magnetar is so intense that it can heat the star's surface to extreme temperatures, releasing vast amounts of energy. This is in stark contrast to normal neutron stars, which, though they rotate rapidly and emit periodic pulses, don't exhibit the same kind of explosive electromagnetic outbursts. One of the most fascinating aspects of magnetars is their relatively short lifespan compared to regular neutron stars. While neutron stars can persist for millions or even billions of years, magnetars shine brightly for only about 10,000 years before their magnetic fields decay. This rapid decline not only makes them rare, but also affects their surroundings. The energetic bursts emitted by magnetars can influence nearby cosmic materials, potentially even triggering the formation of new stars. The study of magnetars provides valuable insights into the fundamental physics governing extreme states of matter, magnetic fields, and the life cycles of massive stars. These enigmatic objects challenge our understanding of the most extreme conditions in the universe. By studying magnetars, we can better understand the mechanisms that drive a range of astrophysical phenomena, further enriching our comprehension of the cosmos. Let us imagine a hypothetical magnetar, magnetar 1b. This celestial object would possess a magnetic field so powerful that it could reach up to 1,000 trillion Gauss. To put this into perspective, this is many orders of magnitude stronger than the fields found on ordinary neutron stars. Earth's magnetic field, in contrast, is relatively weak, measuring around 0.5 Gauss. When compared to the magnetic field of Magnetar 1b, Earth's field seems almost negligible. This immense magnetic force would have a profound impact on the surrounding environment, bending and reshaping the paths of charged particles and influencing the very nature of matter itself. Such a powerful magnetic field could alter the conditions of the stars and planetary bodies nearby, creating extreme electromagnetic phenomena like powerful bursts of radiation. The magnetic field of Magnetar 1b could easily affect nearby celestial objects, including planets, potentially even causing drastic changes to their behavior or atmosphere. If a planet were in close proximity to Magnetar 1b, the effects of such a magnetic field would be dramatic. The charged particles in the planet's atmosphere would become highly ionized, likely creating auroras far brighter and more intense than anything seen on Earth. The surface of the planet could experience massive shifts, especially if it had a metallic core. The powerful magnetic field could affect the geological processes of the planet, influencing the behavior of molten metals, crystallization, and even mineral formation. In these conditions, even materials that would normally be stable on Earth could behave unpredictably. The immense magnetic forces could lead to new and unusual mineral structures or alter the planet's geological composition in ways that defy current understanding. The forces at play in such an environment challenge our comprehension of matter and physics, offering a window into the most extreme phenomena of the universe. As we continue to study these cosmic giants, magnetars like Magnetar 1b hold the potential to unlock new realms of knowledge. By understanding their extreme magnetic fields and the effects they have on their surroundings, we can deepen our understanding of the universe itself, its birth, evolution, and the fundamental laws that govern it. Beneath the intense, almost otherworldly influence of a magnetar's magnetic field, the possibility of a standard atmosphere forming on a planet like Magneto 1b becomes increasingly unlikely. The interaction between the magnetar's magnetic forces and the relentless stream of solar wind could prove catastrophic for the planet's lighter elements. Gases like hydrogen and helium, which are crucial for sustaining an atmosphere, would likely be stripped away over time, leading to a thin or unstable atmospheric layer. Such an environment would be far from conducive to life as we understand it, as a robust, stable atmosphere is often the backbone of habitability. Furthermore, the powerful radiation emitted by the magnetar, combined with its extreme magnetic field, could ignite unusual chemical reactions across the planet's surface. These interactions could give birth to exotic compounds, elements, and materials that, under typical conditions, would never exist. The extreme conditions at play would create a constantly evolving and dynamic planetary environment, far more volatile and complex than what we encounter in more familiar solar systems. The study of such an environment raises profound questions about the nature of life itself, pushing the boundaries of what we consider survivable and how materials can adapt to such extreme cosmic conditions. If Magneto 1b does indeed possess an atmosphere, the consequences of the magnetar's magnetic field interacting with it would be nothing short of extraordinary. The magnetic field reaching intensities of up to 1,000 trillion Gauss would radically alter the behavior of charged particles and ions in the atmosphere. These particles would spiral and dance along the magnetic lines, creating an entirely new form of atmospheric dynamics, one that could produce breathtaking phenomena. The ionization processes driven by the magnetic forces would ionize atoms and molecules in the atmosphere at an unprecedented scale. As a result, the skies of Magneto 1b would glow with dazzling auroras, far more intense and colorful than anything Earth has ever seen. These vibrant displays could serve as a form of communication for any life forms present, or perhaps could act as catalysts for complex chemical reactions within the atmosphere. In addition to the atmospheric ionization, the interaction between the solar wind, a constant stream of charged particles from the magnetar, and the planet's magnetic field would generate a unique magnetosphere. This magnetic shield could provide some protection from the high-energy radiation that bombards the planet, although this might only be effective if the atmosphere were thick enough to hold its ground. If the atmosphere is composed primarily of lighter gases or is thin, the magnetosphere may not be enough to shield the planet. In that case, the solar wind would overwhelm the magnetic shield, leading to atmospheric stripping over time. This would cause the planet to gradually lose its atmospheric mass, altering its characteristics and further hindering the possibility of habitability. The magnetic field's influence would also extend into weather and climate patterns on Magneto 1b. As the ionization processes increase, ion density and atmospheric structure would fluctuate, giving rise to strange, unpredictable weather phenomena. These could include charged particle storms or plasma clouds, phenomena unlike anything seen on Earth, making the planet's climate a violent, ever-changing system of energy and ionized particles. The result would be a planetary environment in constant flux, vastly different from the more stable atmospheres we are familiar with. The dramatic interplay between the magnetar's magnetic field and Magneto 1b's atmosphere would redefine our understanding of atmospheric science. It would challenge long-held beliefs about what is necessary for a planet to support life, expanding our view of habitable environments to include conditions that are far more extreme than anything previously considered. In such an environment, stability would be fleeting, and the potential for life, if it exists, would rely on the ability to adapt to the relentless forces of the magnetar. Yet, the challenges wouldn't stop at the planet's surface. Any spacecraft or electronic device that ventured near Magneto 1b would face extreme and potentially catastrophic conditions. The magnetar's magnetic field would be so intense that it would pose a serious risk to the spacecraft's electronics, interfering with navigation, communication, and data processing systems. A phenomenon called magnetic induction could induce currents in electrical circuits, triggering voltage spikes capable of damaging or disrupting critical systems. These malfunctions could render a spacecraft entirely inoperable, leaving it vulnerable to cosmic forces beyond human control. To shield against these risks, spacecraft would need specialized designs, using materials and electronics robust enough to survive such an intense magnetic environment. Standard electronics would be inadequate, and any failure could lead to disastrous consequences for missions to this strange world. Furthermore, the radiation emitted by the magnetar, including bursts of X-rays and gamma rays, would present another major hurdle. This radiation is capable of eroding materials and damaging electronic components, making it a significant threat to the integrity of spacecraft. Extensive radiation shielding would be required, adding weight and complexity to the spacecraft's design. Such shielding would need to be both heavy and durable, potentially impacting the efficiency and performance of the mission. In the end, while Magneto 1b might appear as a fascinating object in the cosmos, its extreme environmental conditions would make it an incredibly challenging location for exploration, and perhaps the most extreme frontier in our search for life beyond Earth. Space exploration is an endeavor that constantly challenges our understanding of the universe. When considering the proximity of spacecraft to a magnetar like Magnetar 1b, scientists must consider far more than just the distance. The dense mass of a magnetar, coupled with its powerful gravitational forces, would create a turbulent environment requiring highly precise trajectory calculations and sophisticated maneuvering techniques. This intense gravity would drastically affect the path of any spacecraft attempting to navigate its vicinity, demanding the very best in navigational engineering. However, the challenges are not limited to gravitational forces alone. The environment surrounding Magnetar 1b is a true test of technological endurance. Extreme magnetic fields, several orders of magnitude stronger than those found on Earth, combined with intense radiation, would wreak havoc on most conventional electronic devices. This presents a considerable problem for spacecraft design, pushing engineers to innovate beyond current limits. To survive in such a hostile environment, spacecraft would need to be equipped with state-of-the-art navigation systems capable of managing the complex interactions between gravitational anomalies, magnetic disturbances, and radiation exposure. These systems would not only require precision, but also a layer of protection against the hazardous radiation that pervades the region. In the face of such a threat, designing protective measures is no easy task. Innovative engineering solutions would be essential, from radiation shielding to electromagnetic interference filters, to ensure that spacecraft can remain operational and functional. The exploration of these extreme astrophysical environments could potentially yield breakthroughs that apply to a variety of future missions, preparing us for journeys deeper into the unknown. While the technological challenges are daunting, the impact on potential life forms, if any, near Magnetar 1b would be just as profound. The extraordinary magnetic field surrounding the Magnetar could create an environment where life, as we understand it, might not thrive. Magnetic fields hundreds of millions of times stronger than Earth's could affect the very building blocks of life, disrupting biochemical processes and potentially breaking down organic molecules. The intense ionization in the atmosphere, created by charged particles interacting with the magnetic field, would introduce high levels of radiation, making it incredibly difficult for life to exist in any form we recognize. However, there's a fascinating possibility that such extreme conditions might foster the emergence of life forms radically different from anything on Earth. Just as life on our planet has adapted to the most extreme conditions, such as in the depths of the oceans or around nuclear reactors, organisms near Magnetar 1b could evolve entirely new biochemistries. These life forms might harness the energy released by the Magnetar's magnetic field, using it to fuel their cellular processes. Some theorize that life forms on this planet could even evolve ways to protect themselves from the radiation, potentially developing bioluminescent features or reflective outer shells as a defense mechanism. Even more intriguing, certain species might evolve to exploit the magnetic field itself. Much like the magnetotactic bacteria on Earth, these organisms could incorporate magnetic particles into their cells, allowing them to navigate or mitigate the environmental effects caused by the powerful field. In addition, the presence of charged particles could give rise to unique atmospheric phenomena, such as plasma storms, that may impact the habitats where life might exist. If life could adapt to Magnetar 1b's extreme magnetic conditions, the unique behaviors of these organisms would provide a tantalizing glimpse into the broader possibilities of life beyond Earth. The potential for complex ecosystems, however alien, to develop in such an environment opens the door to new fields of astrobiology, where life could take on forms we have yet to imagine. The visual spectacle around Magnetar 1b would be equally extraordinary. With its magnetic field and energetic emissions, the planet would be a living canvas of ever-changing phenomena. One of the most stunning features would be the auroras, born from the interaction between the Magnetar's radiation and the charged particles that permeate the planet's atmosphere. Unlike Earth's typically green and red auroras, those around Magnetar 1b could showcase a much broader spectrum of colors, reflecting the unique mix of particles in the atmosphere. Alongside the auroras, the constant ionization of the atmosphere could give rise to plasma storms, a phenomenon unseen on Earth. These storms could produce brilliantly glowing clouds, lighting up the sky with a constantly shifting array of colors and shapes. Lightning-like discharges could occur, creating energetic storms that would captivate anyone lucky enough to witness them. On the surface of the planet, these storms might leave behind distinct geological formations. If Magnetar 1b has a solid surface, it is likely that its extreme magnetic forces would influence mineral formations, perhaps even allowing for the creation of exotic compounds not found on Earth. These minerals could result in unusual textures and colors, creating a landscape of strange beauty, shaped by the powerful interaction between geological and magnetic forces. In conclusion, the environment around Magnetar 1b is one of extremes, an astrophysical battleground where only the most advanced technologies and the most resilient life forms might survive. The challenges it presents may seem insurmountable, yet the possibility of life adapting to these conditions, combined with the awe-inspiring phenomena it generates, opens up vast new frontiers for exploration and understanding. For now, Magnetar 1b remains an enigmatic world, teeming with both danger and potential, waiting for future explorers to uncover its many secrets. Furthermore, if life forms were to exist on Magnetar 1b, their interaction with the planet's extreme environment could give rise to visible phenomena unlike anything seen on Earth. These organisms might glow with bioluminescence, their bodies emitting radiant patterns in response to the planet's intense magnetic fields or high levels of radiation. Such biological displays would not only add another layer of beauty to the planet, but also highlight the profound connection between life and extreme physical forces. Against the backdrop of Magnetar 1b's tumultuous skies and shifting surface, the planet would undoubtedly offer an awe-inspiring spectacle, an active stage where the forces of magnetism, radiation, and potentially exotic geological or biological activity unfold before our eyes. This dynamic interplay would challenge and deepen our understanding of the laws of physics and raise new questions about what makes a planet truly habitable. Studying planets with extreme magnetic fields like those surrounding magnetars requires cutting-edge methods and highly specialized tools, each one tailored to capture the unique signatures of these extreme environments. One of the primary approaches for studying such celestial bodies is through observational astronomy. Astronomers use powerful telescopes equipped with sensors designed to detect specific wavelengths across the electromagnetic spectrum. Radio waves, X-rays, and gamma rays are of particular interest as they reveal the energetic processes that occur around magnetars and any planets caught in their magnetic sway. These wavelengths provide a window into the highly energetic interactions taking place within the magnetar system, offering insights into the forces that shape the planet's environment. Another essential technique for understanding these far-off worlds is spectroscopy, a method that allows scientists to analyze the light emitted by distant celestial objects. By examining the absorption and emission lines within the spectrum, astronomers can decipher key details about the chemical makeup and physical conditions of a planet's atmosphere. For example, shifts in these spectral lines can point to the presence of ionized elements or other phenomena induced by the planet's extreme magnetic environment. This spectral data can then be used to infer the nature of the planet's surface conditions, giving researchers an idea of whether it might be hospitable to life. In addition to these indirect observations, space missions equipped with magnetometers are employed to measure magnetic fields directly. These highly sensitive instruments detect fluctuations in the magnetic environment, helping scientists chart the strength and structure of a planet's magnetic field. By mapping how the magnetic field interacts with the surrounding space, researchers can gain a deeper understanding of the planet's internal composition and the ways its magnetic environment affects its atmosphere and surface. Further insights can also be drawn from studying exoplanets in relation to their host stars. Observing flare activity or radiation emitted by the star can help scientists gauge the impact of the star's extreme radiation on nearby planets. This kind of data, collected through telescopes and missions focused on exoplanet research, enables scientists to build models that explain how intense magnetic fields could shape a planet's atmosphere, geology, and potential for harboring life. The study of exoplanets with extreme magnetic fields thus requires a comprehensive approach, one that blends multiple observational techniques and advanced technology. This multidisciplinary effort is advancing through international collaborations and the continual development of new instruments and methodologies. As we push the boundaries of our technological capabilities, our understanding of these enigmatic planets and their unique environments expands, offering us glimpses into the deeper forces that govern the cosmos. In particular, studying Magnetar 1b could provide revolutionary insights into the boundaries of planetary magnetic fields and the fundamental processes behind their generation. One of the key lessons to be learned is how an extraordinarily powerful magnetic field influences a planet's structure, atmosphere, and potential for supporting life. By examining the interaction between such a magnetic field and the planet's environment, scientists can better comprehend the role magnetic fields play in planetary habitability. The intense magnetic forces at work could either aid or hinder the planet's ability to retain its atmosphere, offering a valuable case study for understanding how magnetic fields shape the environment of planets both near and far. Another major aspect of this research involves studying the mechanisms that generate such extreme magnetic fields in the first place. The internal processes responsible for producing and sustaining a magnetar's powerful field are a critical part of planetary science. Understanding the dynamo processes that fuel these fields could reveal new insights into the conditions necessary for magnetic field formation in planetary bodies. How Magnetar 1b maintains its extraordinary magnetic field could offer vital clues about the limits of current dynamo theory and help establish the parameters needed to sustain magnetic fields on a planetary scale. Furthermore, studying the environmental challenges posed by such extreme magnetic fields can help define the threshold at which magnetic fields cease to be effective at shielding planetary atmospheres. For example, the protective role that these potent fields play in safeguarding the planet from radiation or solar winds could be crucial for understanding the factors that influence the preservation of atmospheres. These findings could have broader implications, shedding light on similar processes occurring on other planets, including those within our own solar system. Insights into how magnetic fields prevent atmospheric stripping, or how they interact with radiation from nearby stars, could reveal key factors that determine a planet's ability to maintain a stable atmosphere and support life. As we push the boundaries of our knowledge and technology, studying planets like Magnetar 1b is pushing the envelope of what we thought was possible, expanding our understanding of life in the universe, the extremes of planetary environments, and the magnetic forces that make it all possible. Exploring the enigmatic world of Magnetar 1b holds the potential to unlock a wealth of groundbreaking discoveries. In particular, the study of this unique celestial object could reveal novel materials and chemical reactions shaped by the extreme magnetic fields it generates. Understanding how these powerful forces influence mineral formation, chemical processes, and potentially even biological functions could dramatically expand our knowledge of what is required for life to exist and adapt under extraordinary conditions. By delving into the mysteries of Magnetar 1b, we not only challenge and enhance our comprehension of planetary magnetic fields, but we also open new avenues for rethinking the very nature of habitability, geological processes, and life itself in environments far beyond Earth. This research has the power to redefine our understanding of planets across the universe, pushing the boundaries of planetary science and astrobiology. Magnetar 1b stands out as a remarkable example of a neutron star, distinguished by its incredibly powerful magnetic field, several million times stronger than that of an ordinary neutron star. This immense magnetic force originates from the unique conditions within these highly compacted celestial objects, which are the remnants of massive stars that have collapsed during supernova events. Over time, this magnetic field fluctuates in intensity, weakening as the star ages and gradually loses energy. As Magnetar 1b continues to evolve, a variety of factors will contribute to the changing strength of its magnetic field. The internal dynamics of the neutron star, particularly the movement of conductive materials within its core, play a crucial role. Moreover, the intense magnetic field can drive structural changes within the star, affecting the distribution of energy and consequently influencing the field's strength. Some models even suggest that these fields may experience bursts or spikes of activity, causing temporary surges in magnetic intensity. The future of Magnetar 1b is equally fascinating. After millions of years, this magnetic powerhouse will eventually transition into a regular neutron star, its magnetic field gradually dissipating over time. As this occurs, the star will cool considerably, losing the high energy emissions that characterize magnetars. This cooling process will lead to a more stable state, although the residual effects of its once formidable magnetic presence will continue to influence the surrounding environment. Over time, Magnetar 1b, like all stellar objects, will face its eventual end. It may cool to such an extent that it no longer exhibits any active characteristics, marking a dramatic shift in its life cycle. This transformation serves as a poignant reminder of the life cycle of cosmic objects, illustrating how even the most extreme entities in the universe evolve and change across vast stretches of time. The intricate dynamics of Magnetar 1b's magnetic field offer a fascinating glimpse into the complexity and wonder of our universe. In parallel, the concept of Chronos flux introduces a highly theoretical yet captivating area of study in cosmology. Rooted in advanced theories that seek to understand the nature of time, Chronos flux proposes to amplify the effects of gravitational fields and the very fabric of space-time itself. According to Einstein's theory of relativity, time flows differently depending on the strength of the gravitational field. Near a massive object, such as a black hole or a dense celestial body, time slows down relative to regions where gravity is weaker. Chronos flux could intensify this effect, resulting in even more pronounced time dilation near such cosmic objects. As time behaves differently in varying gravitational environments, Chronos flux might deepen our understanding of how time behaves under extreme conditions. Equally intriguing is Chronos flux's potential connection to velocity. As an object approaches the speed of light, time for that object slows relative to an observer at rest. This concept, known as time dilation, is a fundamental principle of Einstein's special theory of relativity. Chronos flux could amplify this interaction, leading to even more dramatic differences in the passage of time between objects moving at varying speeds. This exploration of how gravity and velocity influence the flow of time offers new possibilities for understanding the very nature of the universe. In both cases, whether examining the magnetic dynamics of magnetar 1b or the theoretical underpinnings of Chronos flux, our current understanding of the universe is poised for a profound shift. These investigations challenge long-held assumptions, pushing the boundaries of what is possible in planetary science, astrophysics, and our understanding of the nature of time itself. Ultimately, the pursuit of these cosmic mysteries may reveal far more than we ever imagined, fundamentally altering our perception of the universe and the forces that govern it. Time, as we know it, has always seemed like an unchangeable constant, steady, reliable, always marching forward. But what if this fundamental aspect of our universe could be twisted, stretched, or even broken? The intriguing possibility of Chronos flux, an exotic phenomenon potentially involving unusual matter or bizarre energy states, pushes the boundaries of our understanding, challenging everything we thought we knew about time itself. Imagine a world where time doesn't behave the way we expect it to, where the usual rules of gravity and velocity no longer apply in the same way. This is the territory that Chronos flux enters. It's a place where the very fabric of time and space could be warped, leading to profound consequences. If such a phenomenon exists, it might be capable of altering the flow of time in ways that go beyond our wildest imagination. Scientists and cosmologists remain deeply fascinated by the implications of Chronos flux. This anomaly might hold the key to unlocking some of the most fundamental questions about the nature of time and its relationship to the universe. What would it mean for time to move differently on the surface of Chronos flux compared to Earth? How would life, experience, and existence be fundamentally altered by this shift? The first clue to understanding this mystery comes from Einstein's theories of relativity, which tell us that time and gravity are intimately connected. According to general relativity, the stronger the gravitational pull, the slower time moves. So if Chronos flux exerts a powerful gravitational influence or harbors strange properties that warp spacetime itself, it could create dramatic effects of time dilation, where time slows down drastically for those on its surface. For anyone living on Chronos flux, time wouldn't tick at the same rate as it does on Earth. While mere minutes or hours might pass for someone on Chronos flux, days or even years could unfold back on Earth. This difference creates a stunning, almost science fiction-like scenario, where residents of Chronos flux could experience a form of time travel into the future, effectively skipping forward in time compared to those left behind on Earth. But it doesn't stop there. The effects of time dilation could be compounded if Chronos flux interacts with high-velocity elements or is subject to extreme cosmic forces. Imagine a scenario where an object is moving at speeds close to the speed of light on the surface of Chronos flux. The result would be a drastic alteration in the perception of time. Time would pass even slower for the object moving at such high velocities, further amplifying the time difference between Chronos flux and Earth. This could create a situation where someone traveling to Chronos flux returns to find that much more time has passed on Earth than they experienced, leading to a fascinating form of time disparity. In this world, time would no longer be the constant, predictable force that governs our lives. Instead, it would be a flexible, fluid concept, subject to the influence of exotic matter, high velocities, and gravitational anomalies. As the study of Chronos flux unfolds, it may offer profound insights into the very nature of time, space, and the universe itself. What we once thought of as fixed and unyielding might in fact be something far more malleable, opening the door to new frontiers of scientific exploration and understanding.